Should I use the microphone? Okay, so I should use that. Okay. Good morning, everybody. So we'll start our first parallel session of the JuliaCon. And tomorrow I think we have 2 talks. And the first talks will be given by Giovanni Pagliarini from the University of Ferrara, Italy. And Giovanni will talk about third millennium symbolic learning with Sole.jl. So Giovanni, please.
Hi, can you hear me well? Okay. So, my name is Giovanni and I'm a PhD student in AI in Italy. And together with the people that I work with, we are pretty passionate about Julia. We have been using it for 3 years, and I'm pretty excited to be here to showcase our work. So essentially, I'm going to present this framework of our own creation for symbolic learning. The name of the framework is Sole. In this context, when I say symbolic learning, I mean that part of machine learning, let's see, that deals with models that are inherently based on formal logical languages. And the most commonly known example of such models is the decision tree. These models are especially interesting in contexts where the application of uninterpretable AI models raises ethical concerns. So these techniques, more specifically, can learn models that are transparent in nature and that you can understand how they get to given conclusions. So in order to explain this, I will consider a decision tree and a neural network for an example of a classification task. So I have a classification data set where each instance is a patient described, a patient in a hospital, described by a set of scalar values. And the task is that of classifying the patient as sick or healthy. So let's say I have trained a neural network for this task. When a new instance comes and I have to classify it, I input the information in the input layer, but then the input information kind of ends up permeating the whole structure of the network, so it gets really difficult to understand why the network gives a certain outcome. Instead, if we use a model such as a decision tree, the instance is essentially an object onto which we test certain conditions, and each test is either, each condition is either true or false on the instance. So the instance kind of travels compactly throughout the model so that you can tell exactly why a given classification was given. So this can be really interesting because you can really, you can extract classification rules such as this one. An expert, in this case, a doctor might look at this rule. They might learn, acquire new knowledge. They might modify the rule if it doesn't comply with certain medical standards. These kind of techniques have their own roots to the 80s, basically, with expert systems and with the famous CART decision tree learning algorithm. But they have been kind of overshadowed in the past 20 years because of the deep learning revolution. And today, it appears that they have been kind of relegated to the realm of tabular data. So the question is, what do you do when you have more complex data? When, for example, your patients are described as a multivariate time series, or, for example, as described by an image that is the scan of the brain. Well, what you do usually, what you would do if you want to use a decision tree, for example, in order to achieve interpretable modeling, is you extract feature representations of the image. So you basically represent an image via a set of scalar values, so that you can basically fit a data set of images into a tabular form. And then you can train a decision tree that makes decisions according to those computed values. For example, with an image, you could compute the minimum and maximum value for each of the color channels. You can even trade some simplicity of this model for higher performances if you use, instead of the minimum and maximum functions, more complex features. For example, features tailored for computer vision tasks. But the idea, our idea, would be that when you have this kind of data in your hand, instead of destroying it and simplifying it that much, you would like to perform some kind of spatial or temporal reasoning. For example, it would be nice to express some rule, some classification rule, such as that if in the image there exists a region with a lot of red color, partially overlapping with another region with another characteristics, such as the little green color, with an inner region with a lot of blue color, then this patient is sick. So, but in order to extract this kind of, and to perform this, to express this kind of reasoning, we need to take a step back and lay out the logical foundations of this flavor of symbolic learning. So we've built a set of packages, starting with a package for representing logical formulas and checking their truth on the logical interpretations. Then we've built a package for representing non-tabular datasets. And finally, we have a package where we define what symbolic models are. This is the Sole framework. We are also working on other packages, for example, for post-hoc analysis of the extracted algorithms. And at the moment, the only learning algorithm is implemented in this package, which implements like a cart-like learning algorithm for that can natively perform spatial and temporal reasoning on this kind of data. So now I'm going to talk about the logical foundations and the core concepts behind Sole. And we'll start with a perhaps novel view on traditional symbolic learning. So the first point would be that decision trees, such as the one that I've showed earlier, are inherently based on the simplest logical formalism, which is propositional logic, which we probably all know. Given a set of propositions that represent facts that may be true or not, we can say that a propositional logical formula comes from this grammar. So we can have formulas such as P, not Q, not P and Q. And these formulas can be checked on structures that we call logical interpretations, which sort of assign truth values to the propositions. At the propositional level, an interpretation is exactly a mapping from the set of propositions to values that are true or false. And we can define the truth of a formula, so we can say that a formula is true on a propositional interpretation via a set of very simple rules, so that we can say that, for example, this formula P is true on this interpretation because you have a true value for it, and this formula, not P and Q, is true on this interpretation. We follow this truth-checking algorithm. Okay, so in Sole logics, basically, we have the concept of a proposition, which is essentially a wrapper around anything you want. It could be a string or an integer. In this case, I'm going to, so I have instantiated two propositions, P and Q, and I show that I can manually compose a formula. Then I can instantiate a propositional interpretation, assigning true to P and false to Q, and I can check the formula on the interpretation. Formulas can also be parsed from string or generated randomly. So this is like the most abstract layer of Sole. I haven't given a meaning to the propositions. They're just names as far as I'm concerned. But in propositional symbolic learning, what you do is you interpret a tabular data set on a set of scalar variables. So, for example, the classification data set that I've showed earlier, as a set of logical interpretations, where the propositions are scalar conditions on the values of the variables. So let me go back. If you have a variable such as this one, for which you have numerical values, you can produce a set of propositions, and each instance in the dataset is actually, it holds a true or false value for that condition, right? So a decision tree then, such as this, is nothing else than sort of an if-else, a nested if-else structure that repeatedly tests the truth of these conditions on the instance. I can extend this and say that, in general, you could have formulas here, and that the functioning of this model is strictly tied to the definition of of truth of a formula on a given interpretation. So then I can define symbolic models with this in mind. In Sole, we have two basic blocks for symbolic modeling, which are symbolic models as well. The branch, which is sort of an if-then-else block. It outputs a given outcome if the input satisfies, so if a formula is true on the given input and a different outcome otherwise. And the rule, which is kind of the same, but it doesn't really have an answer in the negative case. So it looks like this. And I call the formulas to be checked antecedents and the possible outcomes, the consequence of these objects. So in Sole, for example, the branch, I can model it as an object that have an antecedent, two consequence, and an info structure holding additional information, such as the accuracy for this model, in the case that it was learned. If you look closely, the consequences are actually of the same type of these objects, abstract model. And this is because you can you can allow consequence to be other models, and you get more complex structures. What is a decision tree if not a nesting of branches? So yeah, we define the decision tree in this way. And once again, the semantics is pretty straightforward. In this case, you enumerate all of the root to leaf paths, and you check for the conjunction of all of the formulas that you find along the path. A decision list is another symbolic model. I don't know if I have the time for that. So I'll just keep on going. But yeah, the point is that all of these models rely on the possibility of saying that a given formula is true on the input, right? And if, so a logician may look at this theory of symbolic modeling and say, wait a minute, none of this commits to propositional logic. So propositional logic is just one, it's really the simplest of all logical formalisms. But in general, you could use different logical formalisms, and as long as you have a way of telling whether a formula is true on a given logical interpretation of that logic, then you'll be fine. You can use these symbolic models. And if propositional logic is not expressive enough to talk, in relational terms and say there exists a region in this image, blah, 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 then I can look for other logical formalisms. So if you want to express concepts in relational terms, one would say that the most natural choice is first-order logic. Yeah, indeed, there is a subfield of symbolic learning which is called inductive logic programming that is based on this logic. But we argue that there is a middleman between these two that represents a better trade-off between computational complexity and, let's say, expressive power. So modal logic is still able to express concepts in relational terms. You can say there exists something that has a given property. But, for example, the truth-checking algorithm for it is much more gentle in complexity terms. What is modal logic? Well, you consider a propositional logic, and you equip it with two new logical operators, which we call the diamond and box operator. So you can have formulas like diamond Q or diamond P and box Q. And instead of interpreting these objects on propositional interpretations, that is, mappings that assign true or false values to the propositions, we actually interpret them on graphs of such structures. So model interpretations are so-called Kripke structures, which have a frame, which is essentially a directed graph, where each node is called a world, and the relation is called accessibility relation, so that you can say that world 2, for example, is accessible from world 1. And each world, each node in this graph, has its own assignment of truth values to the propositions. Okay. So then the truth of a formula is relativized to a given world. For example, I can say that P is true on W1. I can say that P and Q is true on W2. And what about the two new logical connectives? Well, they act as sort of quantifiers across the accessible worlds. So if I say that diamond Q is true on W3, That's because there exists at least an accessible world where Q is true. In this case, W5 assigns true to Q. So diamond Q is true on the third world, W3. Conversely, with the box operator, you're not saying there exists a world, but you're saying every world that I see has a given property. So on W1 here, box P means every world that I see has a true value for P. So essentially, I am able now to express some form of quantification. Maybe I'll skip over this part, but yeah, you can use SoleLogics for checking model formulas on Kripke structures. For example, here, what I did is I instantiated the example Kripke structures, and ultimately I am checking the truth of that formula on each of the worlds of the structure, and I find that it is true on 2 out of 5 worlds in the structure. So how does this help with the learning? This is very abstract. So the key fact is that I can think of an image, in general, an image or a time series, as a Kripke structure where the worlds are regions or geometrical entities on my non-tabular object. So, for example, if I consider a time series, I can think of worlds as intervals in the time series, and for an image, I can consider rectangles in the image. But then I have to I have to give a definition of propositions. What does it mean that something is, what can be true or false on a region in an image? Well, a region in an image and an interval in the time series, they essentially are an image and a time series, respectively. So I can do the same thing that people do when they extract features from an image, but I can do it in the specific worlds. So I can consider a set of propositions that are conditions on extracted scalar features. So I can compute, for example, the minimum of the I can say there's a lot of red if I compute the minimum of the color red in this image within this specific rectangle. And yeah, so I can say that in this region there is a lot of red. Then I have to come up with a relation. What is the accessibility relation here? Well, if I'm thinking in terms of intervals, I can consider, for example, relations from interval algebra, or with rectangles, I can consider relations from region connection calculus, such as disconnected, externally connected, or partially overlapping. But again, I should choose one, so which one do I choose? Well, actually, I don't choose, because I can extend modal logic such that instead of having a single relation and 2 logical connectives, logical operators for it, I actually have a set of relations, and I have a diamond and a box operator for each of these relations. So this allows me, for example, to say that on an image, there exists globally a region with a lot of red, that is where the minimum of the color red is higher than a certain threshold. That is partially overlapping with a different region that has little green, and this latter region has a tangential proper part region with a lot of blue. And this is essentially a formula that I can translate in natural language. So then a symbolic learning dataset becomes a set of model interpretations, that is Kripke structures, and each interpretation essentially has a frame, a graph, which may be, for example, a graph on intervals, in this case. The frame has many relations that allow me to navigate through the object, the image, or the time series. And each of the intervals have a set of pre-computed feature values. And so if I have an object such as this, I can then implement learning algorithms that extract symbolic models based on modal logic that can perform classification tasks on non-tabular data. So here, yeah, I have time to show you the fun part. So yeah, so I'm going to consider a public benchmark dataset for time series classification, and I'm going to show you what you can do if you train a decision tree based on modal logic on it. So this is a dataset with 360 instances, and each instance is a time series of 51 temporal points. And the task is that of gesture recognition. So the input variables, the input 24 variables are the XYZ coordinates of different parts of a person's arm while they perform some gestures. And the task is that of classifying the gesture as belonging to 1 out of 6 classes. Okay, so at a logical level, we can consider an interval-based frame. And for example, if we consider all of the intervals between 1 and 51, we get this number of intervals, which is pretty high. You could even, I mean, you don't necessarily have to consider all of the intervals. You may perform some pre-processing where you try to understand which intervals are the interesting ones. But at the moment, we are going to consider all of the intervals. And on each interval, you compute 24 features, which are essentially, I mean, in this case, I've chosen to compute the minimum of each of the 24 variables. So the neural networks perform well on this task. With the model decision tree, I achieve a 90% accuracy using a 10-fold cross-validation setting. But yeah, so let's see with the code what I can do. So first I import the packages, and I've trained the model using MLJ because model decision trees has an interface for MLJ. So I load the data set, and then I instantiate my model version of CART, which is this model decision tree, telling it to use relations from interval algebra. For example, partially overlapping, or later than, or during. So like I have an interval that is inside me. And I'm telling the model to use minimum as the feature extraction function on each of the intervals. So then I train the model on 10% of the data and test it on the remaining 90%. I achieve an 80% accuracy, but then the fun part is when I look at the model. So I can inspect the model and find that this tree has exactly 6 leaves, which essentially means that it has exactly 1 rule per class. So then with Sole, I can extract the rules, and actually, yeah, I can, so this, I'm not going to go into this, but basically this code is to show the purpose of this code is to show the rules together with the test metrics, for example, the confidence. So in the end, I get a set of 6 rules, 6 non-overlapping rules, and for each rule classifies the instances as belonging to a specific class. For example, the first rule has a confidence of 100%, which means that out of the 25 test instances, 25 instances were all correctly classified by this rule. And so here I can even translate these rules to natural language. This basically says there exists an interval where the x coordinate of the left wrist is less than a certain threshold, and this partially overlaps with another interval where the hand tip, has a different property. I mean, a different position. And then, I mean, with this set, I noticed that 2 out of 6 rules basically have a low confidence. So in this case, these are 2 classes which kind of look the same because yeah, it's all clear, not clear. Basically, it's the same gesture, except you are pointing upwards or downwards with your right thumb. So apparently, the model gets confused, and it cannot tell these two classes apart. Then, I mean, by means of very simple, I just compute the difference between the y-coordinate of the right thumb and the wrist. So basically, I can express the evolution through time of the orientation of the thumb. And if I retrain only using the samples from those two classes, then I get two rules which are a little bit more complex than earlier, but they have confidences of 83 and 95%. Yeah, and so the next step would be to translate this thing to natural language. And of course, this can be hard. In this specific case, I think this rule has a lot of redundancies. So one of the directions that we are going to deepen in the next months is the minimization of logical formulas so that you can reduce their size, or the approximation of logical formulas. And then we are also toggling with neurosymbolic solutions, and we are going to implement different algorithms for extracting decision trees or other kinds of models. So yeah, that concludes my talk, and if this was interesting, I mean, I hope this was interesting. Feel free to reach out if you're interested.
Thank you, Giovanni. I think we have time for one very short question. In the meantime, maybe the next speaker can come up. Yeah. Yes, please.
Just wondering about the learning part. How do you search on this space of all potential predicates and all different ways of connecting them?
So you know the original CART algorithm. Well, it's a greedy routine that starts. You initialize the tree as a leaf, and then you test whether there is a condition that that splits the data set and minimizes. You minimize an objective, which is it can be some sort of entropy with respect to the classes. And at the model level, it's the same. Actually, it's difficult to explain, on the fly, but you essentially have a finite set of possible decisions, and you test each one of them, and you pick just the local optimum. And then you adopt that, then you perform the split, and then you repeat on the children.
Thank you. Maybe one last very quick question. If not, let's thank Giovanni again. So our next speaker is Jad Webe from the Imperial College of London, if I'm right. And he will talk about what's new with ProGradio.jl, which is a projected gradient optimization in Julia. So please, Jad.
Yeah. Hi, everyone. I'm Jad. I'm a PhD student at Imperial College London. And I'll be talking about this package called ProGradio that's written by Eduardo in the crowd over there, and myself under the supervision of Professor Eric Kerrigan. So ProGradio is a projected gradient optimization toolbox. And I guess the first thing I'll talk about is what projected gradient optimization is for people who don't know that. So projected gradient optimization is an approach to solving constrained problems where, say, like in the figure over there, you've got this red triangle in which you've got to remain. So that's your constraint area. And then you've got an initial guess, which is the xk point in gray you see over there. So it's like a two-step approach where you start by computing a descent direction using anything like steepest descent or conjugate gradient, Newton's method, anything like that, to get this green arrow. And you solve step size selection problem to decide how far you move in that green arrow's direction before getting a point that's yk plus 1 you see over there. And then you project back onto your constraint set to get your next iterate. And then you keep doing that until you converge to some optimum. And the reason you'd want to use projected gradient optimization over another form of optimization is because it can be highly efficient in scenarios where it's easy to project back onto your constraint set. So if you've got a box or simplex constraints or some other constraint shape with a cheap projection operator. And so for Progradio specifically, we look at box constraints and simplex constraints. So the reason we're interested in this is because our group does a lot of dynamic optimization, which is this kind of optimization problem where you're solving for functions that minimize an objective over time. So you're not just picking individual points, you're finding functions of time that will satisfy some objective, and then you can discretize these functions to find your solutions, and that gives you really high dimensional problems, which projected gradient optimization is good for. So we do this within the context of what we call Judo, which is this Julia for dynamic optimization organization we have that has Progradio, Intereso, which Eduardo will be presenting on Friday, and a bunch of other packages in Julia. So now that you know more or less what Progradio is, I'm going to talk about some of the changes we've done since last year's release, which are adding a quasi-wolf line search, adding support for simplex constraints, and some problem restructuring work we've done to make things easier for the end users. So what's a quasi-wolf line search? Well, whenever you're doing this step size selection process I talked about, where you decide how far to move in the direction of the green arrow, you basically try and find some step that satisfies some conditions. The most common one is the sufficient decrease or Armijo condition. And that's basically just saying you want your function to decrease by more than a certain amount in that direction. So you want to make progress towards your minimum. And that works, but it can be slow in some cases because you can end up finding very short time steps, very short steps that don't do that much progress, or yeah, you can end up stuck in some loops that just don't help you that much. So the second condition people look at is the curvature condition. And when you combine these two, you have the wolf conditions. And the curvature condition is basically just saying that because you know that as you get closer to your minimum of your optimization function, your gradient has to be smaller. So you look at a certain reduction in curvature at the point you select as your optimum. So doing a wolf line search on an unconstrained problem is very easy. There's lots of established methods to do that. But it's a significantly less obvious thing to do on a constraint problem. And that's why we implement this quasi-wolf line search, which was proposed by Michael Ferry and co-authors in the paper you see referenced there. So I'd love to go deeper into that, but I don't really have the time to. So yeah, I'll move on to how you guys can use this if you use our package. So here's a very simple example where we're solving the Rosenbrock function, which is a standard optimization benchmark. We just define the parameters a and b, and then define the objective function f. We define the function to evaluate the gradient g. And then we define our box constraint through this box object, and then an initial guess, and then we defined our nonlinear program. Then to solve it, we just choose a method to compute a descent direction. So we just choose steepest descent. Then we choose to use a wolf line search and try and find a solution. So it's a simple 3 lines to solve this problem. And then you can see that it goes from taking 139 iterations, if you're using a simple Armijo line search, to only 3 iterations if you use a wolf-line search. You will see, though, that the runtime does not decrease substantially. It's only a 10% or so decrease, because every iteration with a wolf-line search is substantially more expensive than with an Hermite-line search. But you start seeing greater benefit in cases where, say, your gradient G is a lot harder to evaluate than here, where it's like incredibly cheap, and because you like have less function evaluations when using a wolf-line search in general. It will depend on the problem, and some problems are easier to solve with an Hermite-line search, but it's an added tool that can be really useful in some situations. So the other thing we've looked at adding are simplex constraints. So instead of just having boxes, we now allow for, along certain dimensions, the states to sum up to some constant value. And while that may seem specific, it's actually really useful in a wide class of problems. So anything like probabilities, or you know that probabilities have to sum up to 1. We also look at things like mesh refinement that we're interested in for our dynamic optimization problems, where we know that basically when you're trying to discretize a mesh into smaller segments, you know that all of these segments have to cover the full range of the space you're discretizing. And, sorry. And yeah, also things like when you're allocating a finite number of resources to different tasks or different things, you know that you just have a finite number of resources, so they have to sum up to that. And so we now have support for this kind of problem, which you can like solve easily through our approach. And then we did some other small changes where ProGradient now supports any form of abstract array for the states, so it doesn't have to be a vector. You can like feed a matrix input or anything else. We've streamlined the constraint definition, where you can just define a box this way as like a lower bound and an upper bound. And then we've abstracted algorithms to make it easier to specify what combination of descent direction and line search you want to use in a pretty easy way. So yeah, that's it for what we've done so far. In the future, we want to add integration with mathopt-interface.jl to make it easier for other packages to use ProGradio, such as like jump or anything like that. We want to expand our work to more general constraint functions, so we tackle simplex and box constraints explicitly through projected gradient optimization, and then use primal dual barrier functions for more general constraints. And then extend the quasi-wolf-line search to simplex constraints. We currently only support it for box constraints, and then add more search directions, such as quasi-Newton directions. So thank you, and
Thank you, Jad. Maybe we have time for one very short question. Yes, please.
yeah.
So do I understand correctly that the user has to supply the gradient?
Yeah, you have to supply some method to evaluate the gradient. Oh, sorry, microphone. Yeah, you need to like define how you evaluate the gradient. It can be explicitly. You can like define some other way of evaluating the gradient there, but you just have to choose how you evaluate the gradient. You can do like finite difference or something if you want.
So I could just use any multiple
Yeah. Yeah, any function like G exclamation mark that will return the gradient at that point would work. Yeah, no, maybe.
Thank you. Maybe another question, yes?
What happens if you use your quasi-waffle line search in case of box constraints and you cannot find a step size satisfying the waffle constraints within that box because it's too small?
As long as you're starting from a valid initial condition inside that box, it might be a very small step, but there will always be a step. Well, as long as your function is continuous and like well-behaved and stuff, like there are some assumptions on the function, but yeah.
Thank you. Well, let's thank the speaker again. And it's actually the last talk of this session, so if you have more questions for Jad or for Giovanni before, feel free. And see you this afternoon.
Hello. Hi. So there was supposed to be a GPT-3 to understand the Julia ecosystem talk. I came for this, but it looks like Logan Kilpatrick did not show up. So I was very interested in that because, all right, why not? It's 7 more minutes of that time. So I was going to do a project at the hackathon on Saturday, in case anyone is interested in joining in that direction. It would be an operating system built on top of Julia, utilizing transformers, as in a GPT, GPT-3, GPT-4, whichever, plug and play. The idea being, you have an operating system that you communicate with in human language, because we now have an intelligence that is able to translate from human language to code. I've tried this. It works reasonably well. So we can make a framework to say, given any command to your operating system, and essentially what is an operating system? It's a system that gives you access to resources. You have some resources on a network or locally, and computing resources. And you want to ask some question. You might want to say, show me a certain website, or show me the last picture I took last night, or calculate something for me. That's what you do with operating systems, or write a message or send it somewhere. If a transformer can understand human language and translate this into code, and we have underlying the code a all-capable machine, which is a Julia virtual machine, then we can have an operating system with which you talk with. And my idea was that the output of the operating system should give you exactly the information you're looking for. We don't need, so current operating systems, you use Mac OS, Windows, or whatever, you have menus, bars, buttons, and all that. But actually, if I say, show me the last picture I took last night, what I want to see is just the picture, right? And so you can imagine if I say that, show me the last picture I took last night, and that can translate into code like some search algorithm, sort all the files that are pictures from last night, and use a function called open picture. And if we had that, then that would just display the picture. So the end vision of this operating system, it could be called, there's various names, synonyms we could use for this. One idea is essentially it's Magic OS, as in eventually you can tell it to create any app on the fly. In the beginning, the function open picture is not available, is not known to the system. It doesn't exist in the Julia ecosystem yet. But if you describe how that is done, and then you add it to the operating system, you're building block by block ever more and arbitrarily complex functionality into this operating system. Once you ask the transformer to write code for a function called open picture, including the code, but also including a doc string, the description of the function in human language. This then added to the vocabulary of your transformer allows it in the next step to use the function open picture. And so with such steps, and so another synonym for this kind of system would be engineer OS. It's like engineering together, a human together with a transformer is building more and more complex building steps and being able to achieve anything. All right. Right. So if anyone wants to join this experiment or effort on Saturday, I'll be trying this out. It should be, plug and play. Like you put in any transformer you want, anyone that you have access to through an API somewhere, any audio to text transcriber that you have, and then you have this all-powerful Julia virtual computer that can do anything. And we might need something like a human language to regular expression translator to address specific variable names and such. And with that, I'll put it all together. You get what you have in, what was that, Iron Man. You remember Iron Man, where you can just say, open this, zoom top right, close that file, load that website, write this, compute that. You can talk and it will do exactly as you want. All right, thank you for listening.
Check 1 2. Check 1 2. Hey hey. 1 2. Check 1 2. Yeah. Cool.
Seems too quiet in here. Are you the expanding man?
Yeah. Yeah, well, I mean, it's mostly there reading the right files, right? Yeah. Probably, I think the thing I anticipate most complaints about is multi-file stuff, which is part
There is. I have no idea. I can go ask if you want. It's just next to the room. I go ask. So there is an HDMI and there is something to connect. Do you have an HDMI?
I have an HDMI connector, so basically.
Well, there is one here too.
Okay. So maybe just.
Yes.
Is it currently on?
We will try.
Maybe the team. Okay. Yes.
It works. Perfect. Everything's good.
Okay. Perfect.
Oh, and this is. No, you can choose actually HDMI.
Yeah, I'm gonna just do HDMI.
It's just to convert if people don't have.
Are you starting at 210 or at 220?
We will go for 220 because it's the online schedule, yes.
Okay.
Why there is a...
Because I will need the 10 minutes to go to start, but
Okay.
Anyway, okay, I will just stay the first 5 minutes.
Because most people are actually looking online and not on...
Okay.
But then like we told me at the registration desk to actually follow online.
Okay, yeah, it's fine. I will just use this 10 minutes to switch to the start because it's
Are
10
you
minutes
doing it?
Yeah, but later on Thursday.
Oh, okay. Not today.
Yeah, and I wanted to ask, does iPad work fine?
Actually, a Mac works. They have those.
Okay.
Can
Can we check if it's 20 to 20?
Yes.
Yeah, you want me to take out for a second? So if you have a USB-C connector,
I have nothing.
you have no USB-C?
Yes, I have. Yeah. I mean,
Yes.
okay.
Wait a bit.
Okay.
That works. Perfect.
Okay, thanks.
Good. You're welcome.
Yes, I agree. Yeah, my avatar is supposed to look like me, but it's
It does actually.
it kind of
Yeah,
does,
so,
right?
when I
It's
entered,
an
I knew
old.
it was expanding one.
Yeah,
I
it's-
told you, okay, I could make the correlation.
I also feel slightly embarrassed because in the schedule my thing actually says expanding because I put both names because I figured maybe people don't know who the hell Mike Sebastian is.
Parentheses, Michael.
Yeah,
Sebastian.
but nobody else says that, so it's kind of like I'm not trying to be like special. But.
So you started as expanding man, and then you just revealed the name, or how did that work?
Oh, I mean, expanding man's been anywhere I have like a tag or a handle, it's usually expanding man. I've never been like secretive about my name, but it's just usually been expanding man. So I don't know. And in Slack it always just shows the name, right? What's it you on Zula? Are you're in Zula?
I'm
Right?
mostly in Chile.
Oh yeah, you're one of okay. Because there's a lot fewer
I'm
people.
not so super active, but
Right. Yeah. Because there's fewer people on there anyway. So.
yeah, it's more
More
close.
insular, and some of the people I speak to most on there are not here. Like Mason Potter, I speak to him a lot on there. He's not here, unfortunately.
Yeah, I'm not aware. Like it's my first time reacting in real life.
yeah.
So
Yeah. Well, I pretty much same for me. I mean, this is my first JuliaCon. I was at one meetup in the city years ago.
Oh, really?
Yeah.
I know the Zucchero guy. He's also somewhere.
Oh, is he around? Oh, he's one of the people. I was talking to somebody about this before. I don't know his actual name, so I wouldn't know. Is his name Suker? Is that his first name?
No,
or-
it's Valentine.
Is Val? Okay, yeah. So because he's on Slack too. As well.
Yeah, Valentine. Not.
Okay. Because there's a few people who are mostly just by alias, and I don't know who they are. Jar also, whoever that is, he's
I don't know
on
who
Zulip a lot, but I have no idea who he is.
Yeah.
Or she.
Yeah. They.
They.
Good. So you were working on Parquet, right? Yeah.
Yeah.
And you prepared the presentation on Vim.
No, XG Boost. No, it would be nice to have one on Vim, but I don't have it. I didn't really do much in Vim. I have a nice setup that I think a number of people have used, but I haven't really contributed anything.
Oh, how did you make the slides?
Beamer, LaTeX.
LaTeX.
Yeah.
Cool.
Yeah, nice to see. It's weird, like meeting so many people that you've interacted with so many times that you've never met. It's a weird experience, isn't it?
Actually, yeah. Seeing some faces, putting a face to the avatar.
Yeah. Well, I thought Vogamel was so much older for some reason. I thought. Name Mike Sevastio.
Okay,
Mike Sevastio.
Okay, so yeah, I was trying to see those things, so just like nothing more obvious.
No, yeah, physics background, now data scientist, yeah, that's good. Is there, which should I use as a mic here when the time comes? Is there a preferred mic to use? Here, hello.
So you will be on 220.
Yeah, 220 and then there's
I will have to leave
140.
in the last 5 minutes.
Huh?
To change room. I will have to leave in the last 5 minutes.
Oh yeah, no problem. I'm not, I'm not offended.
I was actually happy because you were in 210, which means like I will have 10 minutes after you're done to change rooms because I need to go to the star or the second.
Yeah, no, big. I mean, they're, you know, I think when the talks are down to 10 minutes, they're like more of advertisements than informative anyway, right? It's
very challenging actually to have everything packed in 10 minutes.
well, come to think of it, I had planned to have my timer on here, so I'll do that. Hopefully, won't like this one. I have a little more to say. The XGBoost one is really short. It's not.
And you have another one.
Yeah, I did. I rewrote the XGBoost wrapper, which is gradient boosted decision trees, and a lot of people have helped on that actually. But I like rewrote the wrapper basically. So brief on that. But yeah, I mean this I did entirely myself. So this is probably my most significant contribution, as non-glamorous as it is, kind of. Not even a format I particularly enjoy, to be honest.
Did you do that because of necessity?
Yeah, it's a very important format that you kind of like, you know, certain circles you kind of just can't do without it, and it's, you know, the options around were kind of rough. And at the end of this, I'll actually talk about ways for. I think maybe, well, one of the things I would really like to do is wrap polars. Which
the
is
Rust package
yeah,
for data frames.
yeah, and one of the things that would come with that is loading Parquet. I actually did experiment with this a little, but I'm not a Rust person. I mean, I've a little experience with it by now, mostly just from messing around. And you know, you essentially have to write like an FFI, C interface, and doing that in Rust is
I
not
think
fun.
it's also not super mature at the moment.
Polars?
No, intercommunication between Julia and the Rust.
Well, yeah, there's that JLRS pack. So yeah, so I was looking into it, like maybe not even using that package. Right, so when I looked into it, there wasn't even that much of that package that I could use. I think there's more of it now. Maybe the person who worked on that is here. I'd be interested to hear about that. But, because that would definitely make it a lot easier depending on what capabilities it gives. But, you know, FFI stuff in Rust is not fun. Because essentially you have to break all of the safety assumptions that Rust is built around. And it's not fun. Yeah, and also it's like, it's very hard to figure out how to do things, right? Because if you go online, you look at like what somebody's writing, what a tutorial is, it's like, it's not saying like, okay, do this, and then here's how to do all the things that we just told you not to do. Like it doesn't really give you that information. So it was not fun. Like I've somewhat lukewarm feelings toward Rust. I like it. I mean, I have a lot of respect for it, but you know, it could be a pain in the ass. But you know, certainly like the FFI stuff, I was like, okay, I'm like out of my league here. It's just seemed really painful.
You were mostly looking forward to wrap polars for the Parquet.
Well, that's one of the things. That's one of the side effects I think we'd get out of it.
Otherwise, we have comprehension with data frames.
I think it would be a nice complement to data frames because it actually works very differently. I mean, it's a lot. It would be a lot more like a typed tables kind of thing. Whereas the whole idea behind data frames is like, look, this is a really good trade-off. We could just have generic containers. You know, we rely on kind of runtime dispatch at the very uppermost level for performance, and that works really well. But there are other ways of doing it. And I think polars would be one of those ways that's different, and I think it would complement data frames and stuff more than, well, I mean, it might compete with it also, but I think there'd be uses for it other than, you know, just like not purely just for having Parquet, but that would be one of the nice things to get with it, because
certainly for benchmarking.
Yeah, well, I mean, like intend to maintain this, but it's not like, you know, as far as like big new features and stuff, I don't really know. So, you know, it would be nice to plug into some ecosystem where it's really, really mature. But it's also complicated because if you do it in the most naive way, it'll be very inefficient. Right? Like, I mean, if you load up Python call and just start doing, you know, PyArrow that way, there's a possibility it could be done efficiently with PyArrow because there's a C++ library behind it which uses Arrow, and it's possible for Julia to hook into that in an efficient way. But if you just use it naively, it's going to be horrendously slow. So, you know, that's why it's a little bit complicated. You can't just, you know, and that's, you know, that's why I did this, because it's.
Okay, I will leave you to concentrate.
Okay, thanks. Nice talking to you. I'm sure we'll talk more. Two minutes, right?
Everybody to session of this afternoon. So our first speaker has a PhD in physics from Cornell University, and he's currently a data scientist. So I will. Please welcome Michael Sarastio.
Okay, so I'm going to talk about Parquet, mostly my package, Parquet 2, because this is very short. So for anybody who's not already aware, Parquet is a columnar binary data storage format. It's been around a good while now, about 10 years or so, and it's very popular. It's very, very widely used in certain circles. In particular, if you're doing like quote unquote big data stuff, Apache Spark, that kind of stuff, it's probably outputting Parquet all over the place. So it's arguably finally the thing that's supplanted CSV at a lot of institutions. So brief overview of how it's been available in Julia. First, there was Parquet.jl, which was Tanmay Mohapatra. I saw him at some point in the conference. So he did this very early on, back in 2016, so we've had that available thanks to him. That did not get write capability until 2020. In 2021, I did Parquet 2. Not really any major features on that in the intervening time frame, but this year I rewrote Thrift, which is a different type of serialization format that's used for the metadata for Parquet, and it was a bit of a performance bottleneck, so I redid that this year. So here's just a very brief sample of what it looks like to use this. It's deliberately very mundane. So just write file. It takes anything that's in a tables.jl compatible format. So, speaks the language generally of the Julia data ecosystem. The objects that it outputs are themselves tables.jl tables. This data set thing is what holds the metadata. And you have ways of loading that up lazily. So row groups, which are subsets of rows, or you could load only specific columns. And it's compatible with the normal table stuff. This example is with struct arrays, which I've been using a lot recently, but do data frames or anything else. So brief overview of the features of that. So like I said, it speaks the sort of standard language of the Julia data ecosystem, where it knows that missings are nulls, and it recognizes anything that's tables.jl compatible. As I said, it's lazy by default, so you could load only certain columns. It supports all of the non-hierarchical data types that Parquet supports. So there's quite a lot there. A lot of weird things like weird timestamp formats and stuff like that. There is support for multi-file data sets. It's somewhat limited, but it's there. And right now, snappy, gzip, zstd, lz4 compression, and also understands path strings via file path space. So you can load it from, for example, S3 or something without any trouble. One thing that people ask me about a lot is which format should I use? And so this is a little glib, but the first thing I think you should consider is whether you have something that's already explicitly tabular. If it's not, I think you should maybe think twice before using explicitly tabular serialization format. I think there's a lot of good reasons to use Arrow. So Parquet will never be as CPU efficient as Arrow because it has to do a lot of copying. It has this kind of weird, very null-aware binary format where sort of the positions of data are not predictable, so you wind up having to copy everything. And Arrow also supports compression standards. So again, this is a little bit glib, but I think a lot of the use of Parquet is that there's a lot of people that have to use it all over the place because it predates Arrow, and there are exceptions to this. So if you have data that's mostly null, the Parquet file is going to be a lot smaller. But there's also if it's already gzip compressed, how efficiently is that going to compress the nulls? Maybe very efficiently. So. So that's my summary. I'd say Arrow is pretty interesting, but a lot of times you'll have to use Parquet. Some of the challenges in working on this. So since I first registered this repository, some people opening issues, and there's been a fair amount of trying to deal with edge cases. There's it's kind of a high entropy format, so there's a lot of different ways of describing the same data. A lot of that is, it's necessary. Some of it's not, but there's a lot that can go wrong because of that. For Parquet 2, I've been using PyArrow as kind of the definitive implementation where I'll, insist I should always be able to read stuff that it reads and always be able to write stuff that it can read. And a lot of stuff in the world is from Spark or something else in JVM, but testing with that is a giant pain in the neck. So I haven't done a huge amount of that yet. Some of the samples that are in there are from Spark, but mostly it's been against PyArrow. And a lot of people have opened issues and uploaded files that I've been able to check and fix issues. So that's been really nice. So thank you to everyone who's done that. So outstanding issues, things I'd like to do. So for me, the big issue with this is I don't support hierarchical data types, which Parquet does support, but the implementation is very complicated. It essentially involves a full implementation of this thing called Dremel. And the problem with this is that if you need it right now in Julia, you're more or less hosed. You got to whip out Python call or something because there's nothing that's going to read them. So that's it's kind of an issue, even though the vast majority of Parquet files around might not have it. It would be nice to know that you have recourse if you needed it. Multi-file data sets, it works. It's not great. A big problem is that as far as I know, there's not like a real spec for this. It's kind of weird because it is mentioned in the official spec. There's things that refer to it, but it kind of seems that the implementations more or less do their own thing. I would like to do, be able to do type stable loading, which actually isn't really a big priority for this because, usually you're going to let the schema describe itself, but that's just probably how I would do it if I were going to do it again today. And some other things I'd like to consider, possible future things to do that could touch on Parquet. When I did Parquet 2, there wasn't really good options for wrapping the Arrow C++ library, but now there's this C library, so I think that might be a little more doable. But I think something that's a little more interesting is the possibility of doing it via polars, because I think there'd be a number of advantages to having a really good polars wrapper in Julia. I've experimented with this, but I find that writing in FFI in Rust is unpleasant because you have to essentially violate all of the safety guarantees of Rust. So it would be cool if one of the Rust people were interested in that. Maybe one of the people that were hooting at the mention of it this morning will show up. Okay, so that's it for me. I think Parquet.jl is now a proper subset. There were some data types that last I looked at it were not being handled properly that are in Parquet 2. I don't want to speak out of term on that. It's been a while since I looked at Parquet. I don't know. I don't think much work has been done on it since. It was kind of intended as a replacement, but if Parquet goes on and it's still useful, that's great.
So it's time for the next speaker. So the next speaker is a PhD student in computation and food. So, yeah, do you hear me? Yeah. So he is a PhD student in computation and food analysis, and he now works as at the Royal Military Academy in Brussels. So please welcome Carlo Bonelli, who is going to present synthetic method for food analytics.
Thank you very much. Yeah, this works. Hello, everyone. It's a pleasure to be at JuliaCon. Welcome to the presentation of synthetic eddy method. Thanks for joining me today. My name is Carlo Brunelli, and I'm here today to show you this new package, his features, and how to use it. The package has been thought to be used, of course, in the field of fluid dynamics, where turbulence and its effects are challenging to study till today. And The main characteristic of our turbulent flows are the random fluctuations of their properties, such as velocity and pressure. It's also possible to identify vortices, eddies, and sudden change in the direction of velocity. Understanding and modeling turbulence properly is crucial in many fields of engineering and science. The package aims to do, in this context, one simple thing: to recreate realistic turbulent fluctuations for fluid dynamic simulations. Such fluctuations can be used as boundaries or initial conditions for high-fidelity simulations. Complex flow phenomena depend on how the turbulence and of the turbulence intensity level or their boundaries. For example, for the flow over an airfoil at a low Reynolds, it's deeply influenced by the turbulence intensity, especially when we want to study transition, separation, and reattachment point. We have to proper model turbulence at the boundaries. In fact, this point can shift according to the turbulence levels. I hope this package can help researchers and engineers to have a better match with their experimental results. The features which are currently implemented are, of course, the creation of synthetic eddies. It's possible to choose between different shape functions. The ones that are currently implemented for creating your eddies are the tent, the Gaussian, and the step function. The key features of the package is the ability to recreate a target Reynolds stress tensor, which is provided by the user. So the user, as we will see, has to provide just a Reynolds stress tensor as a matrix, and the fluctuation we will be then creating accordingly. Or the user can, for example, just specify a turbulence intensity level. Often, when studying turbulence, we are in incompressible regime, and this translates into a divergence-free constraint for velocity, and also fluctuations velocity need to respect this condition. So the method and the original formulation has been modifying, and the user can choose to switch on or off this option according to the regime that he is studying. Here you can see the composition of velocity, which can be seen as the sum of two different contributions: an average profile of velocity and a random, local, instantaneous fluctuation. And this last contribution is the one which the package aims to recreate using the following formulation, which is, of course, slightly modified for the incompressible constraint. The idea relies on the idea of the method relies on the creation of a what's so-called virtual box, which is a numeric artifact where eddies are randomly generated, and at every time step they are convected. Once one eddy reaches the end of the virtual box, it's automatically recreated at a random location on the other side. Fluctuations, for example, for the inlet of our computational domain, can be retrieved at any point of our virtual box. But let's see how you can use this package. Synthetic eddy method is a registered package, so you can use it as any other one. The user has to set the eddy's length, in this case sigma, and also the dimension of the inlet plane, for example, where we want to compute the fluctuation, and call the constructor here to create the virtual box. It's also possible to specify different dimensions for the eddies along the three different axes. So eddies can have a different dimension along x, y, and z. When the virtual box is created, it's also automatically computed the number of eddies. And as you can see here, by default, the shape function is the tent function. After the creation of the virtual box, the user has to set the convective velocity. And as we said before, he can specify the Reynolds stress tensor, which is a simple matrix here, and is a symmetric matrix. Or alternatively, he has the opportunity to just write the turbulence intensity. The eddies inside the virtual box needs to be initialized, and this initialization is creating eddies, which is a vector where each eddy is identified by a unique number, by its dimension along the three axes, and by a center. And this center is going to be updated at every time step. And the last properties is epsilon, which is the sign of the fluctuation, which can be 1 or -1. So the fluctuation can be added or subtracted to the mean value. Then we just have to select a point or a vector of points in our virtual box where we want to compute and retrieve the fluctuations. And then simply, as you can see in the example, we can compute the new velocity, which also takes into account the fluctuations, which are computed internally by the package. The properties and the features, let's say, of the package have been also statistically validated. You can see here the spectra that we obtained running the package. The spectra are the one obtained creating the fluctuations for different turbulence intensity level. We can see that the spectra are close to the one of real turbulent flows. In fact, in the subinertial region, the slope is close to the -5/3 trend, which is a well-known trend for turbulent flows. Furthermore, increasing the turbulence intensity level is also increasing the overall turbulent kinetic energy. We can see that all the efforts of creating this package has paid off. In fact, if we compare this spectra with the one that we can obtain just using the random function for creating random fluctuation, we can see that this spectra is flat. It's far from being realistic for turbulent flows. Here, I also tested it for the ability of creating a divergence-free flow, which here you can see the normalized divergence. So it's able to create almost always a flow which is almost divergence-free. And here is just a graphic example of isovelocity contour of fluctuations, which I used as initial condition for studying the turbulent channel case. And here we are at the end. You can see just a sum up of the workflow that I suggest you to follow if you want to test and use this package. I hope this can help engineers and researchers in the field of fluid dynamics. If you have any question, please feel free to reach out. Thank you for your attention. Questions? Yes?
Picture of an airplane in your in
the presentation. Yeah.
Airplane in there.
Yeah, that's the challenge. Yeah. Yeah, you need to create, of course, a really big computational domain. It was just to give an idea of how it could be, how the package could be used. Actually, I'm just studying airfoils. So just for display to put the airplane. As you can see in the example here, I used for an LES of an airfoil and to study how the properties changing the turbulence intensity. This is just one example. Maybe this will be for a talk next year, we will see.
Probably we will keep this speech. So Michael Savastio will again present you the new XGBoost wrapper.
Sorry about that. All right. Hello, hello. So this is on the refreshed wrapper for XGBoost. So for anybody who's not already aware, XGBoost is a really popular C++ machine learning library for mostly gradient boosted trees, gradient boosting in general. If you've done much machine learning, you've probably heard of it. Has wrappers in just about everything. I'm not going to try to explain what gradient boosting is here, but essentially the idea is that at each iteration you train a correction to your previous model. You wind up having to minimize this objective here, which depends on the first and second derivatives of the loss function. So if you have those, you can use a custom loss. So a lot of people have been working on this wrapper recently. It's sort of been an explosion of interest. Tyler Thomas, I don't think I've seen him around, but he did a lot of the binary builder stuff that needed to be done, especially for CUDA, stuff like that. Avik, I think, was one of the maintainers of the package originally. David Widman, I think he did the now CUDA and term are lazily loaded extensions in 1.9, and others have provided a lot of helpful commentary for things to get merged. Jiaming Yuan, I think he is from the main XGBoost repository, so it's been nice to hear from them. So just quick sample of its usage, very straightforward. So when you call XGBoost, it returns this model object, which contains the entirety of the model, which you could use to run predictions, and you could get some useful introspection out of it, such as importance reports. You could get this as an actual table as well as a nice term display there. You can also, I got slides specific on the features, so I'll move on to those. I rewrote this wrapper at some point. It's actually been around for quite a while. So now it uses an automated wrapper of libxgboost from Clang, which is maybe not so much useful for users, but very useful for development on the package. Everything is fully tables.jl compatible. It can track parameters, feature names. The feature names is actually a really useful thing because if you're looking at the trees themselves, it's useful to know what feature is being split on, that sort of thing. That stuff had to be done in the wrapper itself because it's not supported in the C library. There's support for GPUs via CUDA, which again is lazily loaded now. Some nice terminal output via term.jl, which makes these kind of nice, pretty term displays that you saw there. It does support custom loss functions. For the time being, it requires you to provide the first and second derivatives yourself. Again, feature importance. The trees themselves are compatible with abstract trees.jl, so you could do some pretty generic stuff with them, which is nice. There's some default parameter sets there for different types of regressions, classifications. Those were inspired by the MLJ wrapper package, which has the extremely elegant name MLJ XGBoost interface. So you can use it nicely from MLJ as well. I did want to mention real quick that there was, for a little while, this really terrifying bug in Windows that was preventing the libxgboost library from being loaded at all. Myself and some of the other maintainers didn't even have access to Windows, kind of had no idea what to even say about that. So big thanks to number of people, James Foster, Mark, who I believe is up there. I'm not even going to try to pronounce your last name. And Mose of Binary Builder fame, they came in and fixed that, which I can only imagine was, I'm sure the fix itself was just updating a library, but finding it, I can only imagine. So that's fixed now. So as of 1.9.2, you should be able to run it in Windows. If not, please, we closed the issue, so please report it if not. Some other features that'd be nice to have, I'd really like to have automatic loss functions. Like I said, right now you have to provide the first and second derivative. It'd be nice to do this automatically with some kind of, God knows we have enough AD functionality in Julia, so I'm sure we could find some, Zygote or something that should be pretty easy. So I think there's a very good chance that one of us will put that in. Categorical array stuff would be nicer to be a little more automatic. Right now it's a bit of a pain. There's some extra dependencies which are still can't really be gotten rid of. That would be nice when you not using CUDA. Tyler Thomas mentioned to me the multi-GPU support. I don't really know what's entailed in that, but it sounds interesting. We don't have CI/CD for GPU right now. It'd be good to have that so we could have proper tests. There are tests in the suite. You could do it locally if you want. I just wanted to mention real quick. I have nothing to do with Evo trees here, but I've looked at it a little bit since XGBoost. It looks really nice. It looks just about. Again, most people are probably aware, but XGBoost is an extremely mature, popular library. So it's pretty cool that there's a pure Julia alternative that seems, I don't want to talk about their package for them, but I wanted to mention it, and it seemed like an appropriate place because I thought it looked nice. And that's it.
Does anyone have questions?
I don't remember what is the status, but when you talked about these categorical arrays, it came to my mind, what is the current handling of missings? If you don't use MLJ but directly wanted to use XGBoost.jl?
As in, what would it do if you tried to use those right now, or?
Commands that have missing values.
Oh, I don't want to speak out of turn. I vaguely remember, but I'm not confident in the answer to that, so I don't want to say. There are XGBoost does. I think it handles them correctly in that it leaves them out. It essentially doesn't use them when it learns the trees.
Package splits on missingness, so it uses them correctly. It doesn't mess them up, but it doesn't know what to do with categoricals at all.
Yeah. Thank you for that. And I do believe, please open an issue if this is not true. I do believe the wrapper handles that. It's been a while since I looked at that, so I don't want to say something not true, but I think. Yeah. Thank you.
So, thanks to Michael Savastio for his talk. I will now introduce you to Kay Partman, who is a PhD student in solid mechanics at the University of Siegen in Germany. And his talk will be about simulation of fractures and damage with peridynamics.jl. So, welcome to him.
So, thank you very much for the kind introduction. Let me start with the introduction or a short motivation for the topic. So, how does a spaghetti break? If we think of a simple spaghetti and we bend it, so we think it might break into two pieces. So you can try that at home. You won't be able to do that. It will always break in 3 or more pieces. Even the famous physicist Richard Feynman was very fascinated about this problem. So what we have with fracture is prediction is very difficult, but there are methods to simulate fracture, especially paradynamics, and we wrote a package to use that with Julia. So what is paradynamics? Paradynamics is a non-local formulation of continuum mechanics, and it's discretized the continuum with material points. So it's a non-local method, so it means the points interact only inside of a specific horizon called delta, and the set of the points that is inside of this horizon is called point family. So the kinematics from this is, so we have these interactions between these points, they're also called bonds. And if you have a deformation on the body, these bonds have a length change, and which is then used to calculate forces between the bonds, or between these points. So with our Julia package, paradynamics.jl, you can use that to make simulations. We have a few features. First, you can use quasi-static simulations, very basic simulations with the dynamic relaxation algorithm. Then, of course, the main thing, the dynamic simulations, where you can have fracture and damage. With a new version 0.2, you can also have multi-material simulations where each material point has different material properties. And of course, the logo, you can have multi-body contact simulations. So on what we will focus on now is an example simulation using this dynamic framework with the velocity valet algorithm. So basically we need 6 steps to perform the simulation of this spaghetti fracture problem. What you can see here is of the full source code that is needed with the package. And these steps are actually, all included in the source code. We go through that step by step now. So first, after loading the package, we have to define the point cloud. And therefore, a few methods you can do that. The easiest method is to use the readInp function and import a finite element mesh that was defined in abacusreader.jl. That abacusreader.jl is used to import the meshes you define in Abacus. So basically what is done, any finite element is then converted to a point cloud. So when you run this in the REPL, you can see the nodes are found and elements are passed, and element sets are then turned into point sets. In the next step, we have to define material properties. Here we use a simple point-based material. Here the first parameter we have to define is the horizon, which is basically this important parameter of paradynamics. Then we have density, Young's modulus, and epsilon c, which is basically the critical bond stretch that you need to define for the damage. If you run this in REPL, you have a nice output, and you can see additional parameters of the simulation are then calculated within this type. Important thing for this simulation is we have to define boundary conditions. And what we use here are force density boundary conditions. And the setup we use is some 4-point bending setup. So basically we are just bending on 4 points. What we use is the force density with linear increasing amount with time, as you can see here. And as I mentioned before, the point sets we use from the point cloud were defined in Abacus. For the temporal discretization, you can easily define the algorithm. Here we use the dynamic one, the velocity valet algorithm, with 30,000 time steps. And for export settings, we have to define a name and a path where we want the results to be written at. And this 20 means that every 20th time step VTK files with the help of the package write_vtk.jl are written. So, and the last thing, we have to define the analysis type with all the previously defined input parameters. In order to run the simulation, we have then submit the job. We now look at the results. We can see the spaghetti in the bending process. And after a few milliseconds, you can see the cracks form. We take a closer look. We can see some kind of damage on the upper side. And then the first cracks and secondary cracks form. So basically, we have multiple pieces, and these kind of cascading cracks we can see in the experiments. So to sum up, the package paradynamics.jl is able to perform fracture simulations with only 3 lines of code. The current feature set is a solid foundation, but we want to extend that. So for the future development, we plan on releasing no material models and additional discretization features. And one core point, we want to improve the multi-threading performance of the code. And therefore, we welcome you to submit issues, feedback on pull requests to improve the package with us. So thank you very much for your attention.
Have any questions?
What's the largest problem you've used this for? What kind of problem?
Numerically speaking, so we used it on a, it's called Kalthoff-Winkler test with, I think it was 30,000 material points. So it's able to do that, but you can get memory problems, and that's a point we want to improve.
Anyone has any questions? So the next speaker, he is a senior research software engineer at Princeton University at the Data-Driven Social Science Initiative. So his work mainly focuses on analysis of large and complex social science data sets. So please welcome Colin Swaney, which is going to talk about network hoax processes.
Let's see if I can get the right one. Yes, okay. All right, thank you for that introduction. So I'm Colin Swaney, at Data-Driven Social Science Initiative. I'm going to talk about network hoax processes. Like so many Julia packages, the name kind of says it all. We got networks, hoax processes, and Julia. I struggled with a good introduction, and then I was looking through the schedule, and I realized I already wrote a really good introduction in the abstract, so I'm just going to read it. Network hoax processes. It's a pure Julia framework. You can define, simulate, and perform inference on a pretty general class of Bayesian probabilistic models. The key thing is that you can simultaneously perform inference on the structure of a network and an event-generating process. So the two things are combined. This is a framework that was developed by Scott Linderman and some co-authors at Harvard, now Princeton, in 2016. So the key feature of the event-generating process is that it's autoregressive and a multivariate. And then you have connections between nodes given a network structure, and that can be just any standard Bayesian network model that you like. So we combine these things together. It gives us a disciplined way of discovering latent network structure from the event data itself. This can be used in neuroscience, finance, whatever. It's a very general type of model. So I'm going to quickly talk about the package features. and then I'll go into detail on some of these later. So we have a modular design. I've tried to make this so that it would support extensions. If you want to bring your own component, you can do that. It supports both continuous time and discrete time models. It implements simulation via a Poisson thinning process, which I'll talk about. It provides multiple inference methods for all models and accelerates estimation using Julia's built-in multi-threading module. So I'm going to break this into sort of two parts. First, I'm going to describe what the network's Hawks process is, how it works, and go through a kind of recipe. And then I'll switch over to the features of the package. So Hawks process is a Poisson process. It's modeling the arrival of events. And a Poisson process is basically defined by an intensity, which is lambda here. The intensity is essentially telling you how likely it is for an event to occur in a particular period of time. The defining feature of a Hawks process is that it's autoregressive. Every time an event occurs, there's an impact on the future intensity. It increases that. And in this framework, since it's a network, it potentially impacts the intensity on nodes around it as well. So there's an example here, which is a bivariate example. You have a red, one node has a red intensity, the other is given in blue. And what you see is towards the beginning there, you get this sort of spike in the intensity on the red node. And that's because you see every one of the small spikes as an event. So you have a number of events occurring on both the red node and the blue node, both of those contributing to the intensity on the red node. So Hawks processes are good at capturing events where there tends to be spikes or clustering of events. And notice that the intensity is broken into two parts here. So there's a lambda naught, and then there's the sum of H terms. So the lambda naught is called the baseline or background process. It could be a simple homogeneous process with a constant intensity, or it could be something more complex, such as a log Gaussian Cox process, which is a basically exponentiated Gaussian process, so something very flexible. The key here is really that the baseline is largely independent of the rest of the model. So we can sort of pick whatever we want for the baseline. It's going to generate its own events and just do its own thing. All right, so what's the effect of each event? That's captured in an impulse response. An impulse response is essentially just a probability distribution. The traditional one is an exponential distribution, one parameter model. It results in an instantaneous increase in the intensity, which decreases exponentially. A more flexible model is the logistic normal or logit normal distribution, which has two parameters, a mean and a precision. And this allows you to move around this peak. So you can move the mean and adjust where the peak is. You can move the precision and determine how spiky or smooth this impulse response is going to be. The key thing here, though, is that the impulse response is only determining the timing of the effect of each event. Both of these are probability distributions. Anything that you would use should be a probability distribution. It integrates to one, and therefore the overall impact on future events is the same. So in order to have differences in connections between nodes, we need to do some sort of scaling. And we handle the scaling in what's called a spike and slab fashion. So we're going to sort of separate the scaling into two parts. The first part is a binary adjacency matrix, A. Every element in the matrix represents a connection from one node to another node. And then the second part is a weight matrix, a positive weight matrix. The weight matrix captures the strength or the magnitude of a connection from one node to another. So multiplying those together and you get the overall scale. And so if you put everything together, you have an impulse response multiplied times A times W. That's going to represent the overall effect of one node, an event occurring on one node on the intensity of another node. So that's almost everything in the Hawks process. The last part is the network. So the adjacency matrix doesn't come out of thin air. We want a model to tell us where does that come from. And that model can be basically any Bayesian network model that you want. So here's a list of some trivial ones: an empty model, a dense model, a fairly simple Bernoulli model where connections are a constant probability row. And then you have more complex things like a stochastic block model or a latent distance model. The key point is that this model, this network model, really connects to the rest of the overall model only through the adjacency matrix. And so you can sort of choose whatever you want here as long as you have a way of sampling from it and it generates adjacency matrix. All right, so that gives you sort of a recipe for constructing a network Hawks process. And each of the ingredients in that recipe is going to map directly on to a component type in the package. And that allows us to make this package in a nice modular design. So processes are built up from components. You have a baseline, impulse response, network models. As long as your components that you define adhere to a common minimal interface, for example, RAND, resample has to implement these methods, then you can construct a network SOX process from those components and all of the methods that you want, like RAND and estimation methods. These all just work. And there's two sort of main points where I think this is useful: the baseline and the network. So with baselines, we have a sort of small interface. If you define your own baseline and you define the methods here in the interface, then you can use that in the continuous standard or continuous net Hawks process, and it's going to work. There's actually a few things on here which you don't need to define if you don't want to, but the more of these that you define, the more methods that are going to open up to you in the Hawks process. So internally, this was useful. I started by making a simple homogeneous process. The homogeneous process is nice because you have a fast analytical Gibbs sampling that you can perform. However, assuming a constant intensity isn't really a great choice in a lot of modeling settings. Just imagine that you have seasonalities in the events that you're trying to model. Constant intensity is not going to be a great choice. But then using this interface, I was able to define log Gaussian Cox process. And this is an extremely flexible model. You can choose, I have a couple kernels that I've included in the package, but you could choose your own kernels. The disadvantage of this is that it requires a sort of subsampling process for Bayesian inference, which is a bit slower than the analytical Gibbs sampling. All right, so the module design allows you to define your own baseline, and then you can plug that in. The other place where it's useful is in defining your own network. So we actually have a continuous standard Hawks process where I don't have an adjacency matrix or a network model. It's basically just a multivariate Hawks process. If you want to make a true network Hawks process, then you include an adjacency matrix and a network when you construct your model. And the sort of disadvantage here is that you lose maximum likelihood estimation. I'll talk about that in a second. But because, as I mentioned, this network is kind of separate from the rest of the model, you can go ahead and define a new network, and as long as it adheres to the following interface, plug that into the network Hawks process, and everything will run. The networks that are currently available are a dense network and a Bernoulli network. I have some work in progress on the stochastic block and latent distance networks, but I'm not ready to put those in quite yet. All right, so that's the modular design. The other thing is continuous and discrete processes. When the events that you're studying are very dense. So basically, if you have a lot of events occurring per second, a continuous process is going to get bogged down. Especially on inference. For inference, basically, you have to calculate the intensity at every point where an event occurs. And because of the autoregressive nature of the model, that means that you need to look back over the entire history of events. So this is quite slow. To get over that and practice with high density events, what you need to do is switch over to a discrete time formulation. In discrete time, you just make a bunch of time bins, and now you can put all of those events into the discrete time bins. It doesn't matter whether there's one event in a bin or 100 events in the bin now. You just need to know what's the number of events in that particular bin. And as a result, you go from something which is basically on the order of number of events squared to something which is not linear, but actually just constant complexity. So switching over to discrete time is in some cases the only real practical solution here. So we've divided the package into, so at a high level, sort of the abstract type Hawks process. We have a continuous Hawks process and a discrete time Hawks process. Obviously, the continuous and discrete time processes have their own way of representing the data they generate. There's also a whole set of discrete time components that you can use as well. So things work a little bit differently there, but same basic approach. So there's two sort of main things that you'd want to do with this package. One of the things is to simulate data. Essentially, we provide a RAND function where you put in your Hawks process and the duration of how long you would like to simulate the data for, and we can generate that. The process by which we do that is something called Poisson thinning. And if you think about how to simulate this, it's not that obvious, but the Poisson thinning gives you sort of a clever trick, well known in the literature. The idea is like this. The baseline intensity is sort of functioning independent of the rest of the process. So what we do is we start by simulating all of the baseline events. That's the dark blue dots in the image here. And then each of those events essentially makes its own little independent event, which can go off and generate more events. And so we simulate all those little events. They generate their own children, we simulate those, and we have this recursive formulation. So we run that, and then when we get done, we collect everything, sort it, and put it into a nice format. The one thing you might be wondering is, how do we know that that recursive process is actually going to complete? So this might blow up. We provide a little function called isStable. IsStable looks at the parameters of the model. There's a very simple calculation to do on the eigenvalues, and if you check that, it'll tell you whether you actually are dealing with a stable process or not. So that's simulation. So the other, probably the most important thing that researchers are interested in is estimation or inference. The package provides three main methods for doing this. First, we start with maximum likelihood estimation. So this is fairly straightforward. We just use the Optim package, standard gradient-based optimization. Unfortunately, for the network models, you can't use maximum likelihood. You have a binary adjacency matrix, so your gradient methods aren't going to work. So maximum likelihood is limited to models that you might be using as a sort of baseline that don't include a network. The main method of interest is Markov chain Monte Carlo inference, Gibbs sampling in particular. So we have an MCMC method that performs this. Every component that's in the package right now, so all the built-in components, have a resampling method, and that means that they will work with MCMC. So any Hawks process that you could build with the built-in components, you'll be able to run MCMC sampling on. The last method we have is variational inference, and mean field variational inference in particular. So variational inference converts the inference problem into an optimization problem by making some assumptions about the posterior distribution. This method can be very fast, but it is limited to discrete models, and that's simply because we only have a formulation for it in the discrete time model. And I'll mention one other thing about that later. So we have three ways of estimating things, up to 3 ways of estimating things. And when I was talking about the interface, which of these are going to be available is going to depend upon what parts of that interface you define. So if you want to perform maximum likelihood estimation, you need to be able to define a log likelihood for your component. If you want to do MCMC sampling, you need to define a resampling method for your component. And if you want to perform variational inference, you'll have to define a variational update method. So if you have all 3 of those, you can put that component in and you can run any of these on the resulting Hawks process. Okay, the last bit I wanted to discuss here is multi-threading. So resampling is the main thing here. There's a bunch of embarrassingly parallel calculations in the resampling methods. In particular, for Gibbs sampling, the adjacency matrix, instead of sampling each element of the adjacency matrix individually, you can take blocks of it. In particular, you can look at a whole column at a time. Sampling those columns are independent from each other, and so we can just do them simultaneously. And the other sort of important one, the most important one here, is the log likelihood calculation, in particular for the logit normal impulse response. So as I said, in that calculation, you have to look at the intensity at every single event. And that's why it turns out to be sort of order number of events squared. However, those calculations are all independent of each other as well. So I can just go to every one of those events and say, do your own little log likelihood do your own little intensity calculation for your event and do that. And so this is going to scale very well with the number of threads that you throw at it. And in Julia, we have the beautiful @threads macro. And so with a couple lines of code, we can make this, n thread times faster, basically. So this is actually really important because in general, all of these methods are fairly computationally intensive. And as the size of the network gets larger and the number of events get larger, this can be quite slow. So this makes practical what otherwise would be quite difficult, I think. All right, and finally, a few notes on the package status. So I have some work in progress right now. It's basically ready to be merged. I just need to do some final checks. As I was sort of preparing for this, I was looking at making some new examples, and one thing I realized would be nice is, even though this is geared towards network Hawks processes, you want to compare your process to something, a baseline, and for that, it's nice to have an independent process. So a process where we just say everything in the graph all the nodes in the graph are independent of each other. And to do that, it's quite convenient to just make a univariate Hawks process. So I took the same modular design and created a new univariate version of the Hawks process definition in this package. And then I built an independent process. So you can now just directly say, I am making an independent Hawks process. Here are the components, and do that. There are some feature requests. These are my feature requests. I'm looking for other feature requests, but I would like to finish the advanced network models, so stochastic block, latent distance, potentially some time-varying network models. The variational inference I mentioned, that's oftentimes quite fast, but we can make it a lot faster, potentially, by switching to a stochastic variational inference. We don't need to use all of the event data. We can just randomly sample some of it and run the optimization on that. So that should be a relatively simple thing to do. The other thing is exogenous covariance. This is something that every time I talk to social science people, and I say, I have this model, it's so interesting, and the first thing they say is, what about exogenous covariance? So basically, I have a baseline model, and you know, it's sort of independent of the rest of the model. And wouldn't it be nice if I know that there's something else going on outside the environment that correlates with the intensity of the process? Wouldn't it be nice to have that? This should be fairly simple to do. It's with the sort of modular design, it's a matter of defining the correct baseline and getting the inference figured out for that. And then you should be able to plug it in. Finally, there's some utility methods that I need to put in here for evaluating models. Some help on initializing models. So for inference, we always have to initialize things first, right? And I think we could do a better job on selecting initial models or making it easy to initialize them from other models. And maybe some visualization things. All right, so that's it. There is a website for documentation, and also I want to plug the Data-Driven Social Science Initiative. We have a website as well. Check it out or come talk to me. Love to tell you what we're working on. Thanks.
So does anyone have any questions?
Do you have a running example in your mind of like what of a natural phenomenon or say like the stock market would be like a good model and for which the ops process would be a good model?
A good application. So the application I like, this is one of the applications that Linderman used in his paper, was analyzing crime. So look at a bunch of different neighborhoods in the city, get crime statistics, and see, hey, when crime's happening in this area of the city, what's going to happen? Can I forecast what's going to happen in other areas of the city? It's a very interesting application, and it's, you know, a good one.
Response functions that are continuous ones that are defined over a bounded interval, so you don't have to like loop over everything that's happened so far every time you calculate the
The answer is yes, because the logit impulse, logit normal one is actually bounded. Yeah, so that one is bounded. You specify basically what is the look back period. That's a input delta t into that. And yes, it does help, but still, it's better when it gets to really dense events. It's better to have the parallelism. Yeah.
You were mentioning the @threads macro. There's been a lot of discussion about that recently. Have you considered any of the other threading packages as a way to parallelize your code?
I have not explored anything else, and I've had a lot of success using that macro. So for this application, it's fairly straightforward and works very well. So I'm happy with it.
So you have some data and you try to, say in the case of the crimes, and you're trying to, is it possible to estimate what is the impulse response? Like how much, say with the likelihood method, or how much can you try to estimate the parameters of your model?
The whole thing is estimated. So the only thing I'll say about the impulse response estimation is, in some cases it isn't the likelihood basically isn't that responsive to the impulse response. And so you can come up with estimates that aren't that meaningful, I think, in some cases. It's just that the baseline and the weights tend to sort of dominate. That's what I sort of empirically see.
Agency matrix underlying the process is easy to estimate? Like, is it easier, or they like to be a little bit sharper than the impulse response?
Is the adjacency matrix easier to estimate? I don't know if I have I have sort of observed that it doesn't tend to sort of give you probabilities that are very close to zero. So it seems that this is partly because you have to choose a prior for this, right? So maybe with the correct choice of prior, you'll be able to push those probabilities down a little bit more. But mostly what I see is, like, if there is a connection, it's going to give you a probability of 1 or very, very close to 1. And if there's not a connection, maybe it'll be like 0.5. Yeah, but it struggles to push it far down.
And we can welcome our next guest. Is he in the room? Yes, okay.
The starter one doesn't work. I have the. Do you have a room? I'm connected to any room and I have no idea. MIT guest maybe? Do you need? I don't need it, but it would be a little bit better. But I don't need it. Let's do that. We don't have it. Okay, whatever. Do whatever.
Cool. HTML.
So our next speaker is a data science developer at R2, which is a company specialized in development of monitors for the chlor-alkali industry. But most importantly, for this talk, he has held the role of principal maintainer of Plotly.js. So please welcome Etienne Tétropinard, which is going to talk about tips for writing Dash.gl applications.
Sorry about that. There we go. Okay, good. Good afternoon. So here we're going to jump ships and head into the data viz world, and more specifically dashboards, so data science web applications. Can you hear me okay? Oh, it's the wrong mic, okay. So this one here, is this better? Yeah, okay, cool. Okay, so let me start over. So we're gonna jump into the data viz world, more specifically dashboards, so data science, web applications. So my talk is tips for writing and maintaining Dash.gl applications. Okay, so first of all, wait, put this in full screen actually. Okay, this looks better. Okay, it's a big screen. Okay, so what is Dash.gl? So Dash.gl, it's a Julia package. It's the Julia version of Dash from Plotly. So Plotly is a company. Dash is a popular data science web application framework in Python. Dash.jl is the Julia version of that framework. It's open source. In the Julia world, I think the closest framework is Stipple, which is based on Genie. I say similar because they're both fairly high level and fairly tailor-made towards data science applications. And then if some of you know R, it's kind of like Shiny, which has been around for a while now. Okay, so let's get a feel for who showed up. This was a weird block of kind of, left and right talks, so I don't know who showed up to mine. So who has ever used Dash.jl before? So just a quick show of hands. Okay, not too bad. More than I expected. Who's ever used the Python version of Dash before? Quick show of hands, so less people. Okay, that's interesting. Okay. Who has ever used a Plotly plotting library before? Okay, so a lot of people. Okay, good. So those of you that have never used Dash.jl before, don't worry, there's going to be an overview section. And then for you, those of you that have used Dash.jl before, well, we're going to get into some more interesting stuff in the later slides. So I'm gonna, when it comes to choosing a framework, especially when it comes to web applications, a lot of it comes down to personal taste. And I kind of don't want to get into that today, but I still want to make an argument for using Dash.jl. So this is going to be my argument. So why use it? First off, most of the logic is done in JavaScript, using libraries that Dash.jl shares with the Python version of Dash. What that implies is that Dash.jl doesn't actually have that much Julia code. I mean, that's still it's still 3,000 lines if you count them, but for the amount of stuff that you can do in Dash.jl, that's not a whole lot. And then, like I said, so it's based on the same libraries that the Python version uses. And then if you go on PyPy and you look at the Python version of Dash, it has over 1 million downloads per month. That's something that any Julia library would have a hard time doing. So I'm going to go ahead and make this claim, saying that Dash.jl is more robust than the other web UI libraries out there in Julia. This is, of course, a debatable claim, so don't shoot me. Yeah, okay. Next, so why am I giving this talk? So I'm currently working at R2, engineering consultants in the chlorine production industry. So it's the electrolysis of brine. I won't get into the details here, but I guess what I can say is I'm split my time between doing data science and developing data science web apps in Dash.jl. So we're based in Montreal. That's in Canada, if you don't know. Yeah, let me show you a few screenshots of the apps we have internally at R2. So this is all Dash.jl. Some of the stuff you can do. Another screenshot. Okay, so next, there's more reasons why I'm here. So previously I worked for Plotly. Remember, that's the company behind Dash. Full disclosure, so I guess some of you might say that's another good reason for using Dash if you worked for Plotly before. And then last fall, I've met with my former boss, and I told him I was using Dash.jl for work. And he's a nice guy, and he went ahead and gave me write rights to the repo. And then since then, I've made 2 Dash.jl releases. Last one coming a few weeks ago. And then what I'd like to, what I wish out of this talk would be to have more people use Dash.jl, of course. Have more people willing to contribute to the Dash.jl repo. And then if we could get together and maybe start building a new package that would wrap around what's already available in Dash.jl, something that would be more experimental, more Julian. that would be cool also. Cool. All right. So outline. That was the introduction. Next, I'm going to do a quick overview of Dash.jl. After that, I'll show you how to add a simple feature in Dash.jl, just to get a feeling for how the thing scales. And then after that, I'll discuss how to make Dash.jl feel a bit more like Julia. So this is a Julia code, Dash.jl, 25 lines. Already gives you an interactive data science web app. And let me go ahead and show you how that looks. So this is an iframe pointing to a server that I'm running on my laptop. So it's fully interactive. And then this is just, it's kind of hard to do. I should have brought a mouse. But if I go ahead and select a data file, this is going to create a Gantt chart. And then let's say you have multiple data files, you go ahead and select the other one. And then, of course, this is a plotly graph, so if you hover over it, you get the exact values. This is the sort of graph we use a lot at R2. So in industrial settings, the start of a bar could signal the start of an anomaly or a fault. Say your temperature is too high at your plant. And then the end of the bar would be where that condition ends. So then with hover labels, it's kind of easy to tell exactly when something wrong started and ended. All right, cool, let me get started. Let me keep going. So I'm gonna go step by step just to show you how we built a Dash app. So you start with using Dash, then you instantiate a Dash app type with this lowercase dash wrapper. So Dash doesn't ship with CSS by default, so you'll see this external style sheet a lot in the tutorials, but you could have any CSS. Then this app, we'll use it to run an HTTP server. But before we do so, we need to set up a layout. So this is just a combination of HTML components and also more evolved components. So this DCC means Dash Core Components. And this is exported from the Dash module. So here you see we have a drop-down and a graph like we just saw previously. Please notice the IDs set as keyword arguments here. So we're going to use those IDs to add interactivity. So interactivity here, I mean something happens in the front end, so a user clicks or selects something in the drop-down. We're going to use this new value coming from the drop-down to update a component. And in this case, it's our graph. Dash calls them callbacks. And so they work like so. So you need to set an input, which works like a trigger. So anytime the drop-down value changes, this function is going to get called. And then the return value of that function will update the figure property of the graph. And then we're defining this as a do function. So fname will be the value, the file name coming from the dropdown. And then there's a bit of logic. So when you start the app, fname isn't set. It's set to nothing. So you need to handle that case. And that happens a lot. I'll talk more about this later. So this make GAN function, I kind of cheated. So this app is more than 25 lines. This is how the make GAN function looks. This is one way to do it. It's one way to make a GAN chart. Plotly doesn't have a way to make a GAN chart natively, so you need to work around the bar type. So this is one way to do it. And so Plotly graphs are essentially just a big JSON. So you can use any data types that serializes to a JSON. In Julia, I like name tuples a lot. But you don't need, you could use a dictionary or wrapper libraries. I think it's called plotlyjs.jl if you want. But a plain name tuple works, and I find it really nice, especially with the implied keyword syntax. So you can define y base x on separate lines and then just shove them into a name tuple like this. I find it kind of nice. So what happens after that? So Dash will serialize that into a JSON using JSON3.jl. And then this will, then the front end will get that JSON and then render the graph in JavaScript. This is what happens behind the scenes. Okay, so I'm going to show some Python code at JuliaCon. But again, this might be controversial, but this could be helpful too. So this is the exact same map that I showed you. It could be generated using this Python code. And if you look at it closely, or if you paid attention, like it's very similar to the Julia code. That's good, because again, there's a lot of Python Dash users out there. There's a lot of examples online. So if you search for something and you see Python code, after a bit of practice, you could easily translate it to Julia. And most of the time, it will just work. I mean, it's not, not all features will work, but most of the features will work. So we get a lot of documentation for free, just because code just looks pretty much the same. Next tip, so if you're looking for something, some interactivity, and you don't know the property names of your components that you want to update, the Julia REPL is one nice way to get that information. So next, we're going to add a feature. We're going to use the click data coming from DCC graph component. And yeah, so the Dash REPL is a nice place to get that sort of information. Okay, so next 15, okay. So yeah, so like I said, we're going to add a feature, see how this thing scales. So what we want to do, we want to handle the click data coming from the graph. We're going to add some HTML to the layout, and then we're going to add another callback. Here, this has a different, what's that? Not yet. Okay, so this callback has another little dash type in there called a state. So a state will not trigger the callback. It's just the value that your callback can use. But the callback isn't going to get triggered whenever that thing changes. In other words, this callback gets triggered whenever we click on the graph. And in that callback function, we'll also check and use the file name we selected in the dropdown. And to start, we're just going to make a string out of it and see what kind of result we get. We're just building this app interactive step by step. So if again, pretty tricky to do. Select this B type, and then the click data will show up here. Okay, so you get some information corresponding to the bar we just selected. We just clicked on, sorry. And then if you click on a few different bars, the thing changes as expected. So now what we like to do, we like to make something more interesting out of this click data. So let's say instead of just outputting a string, we use this click data to generate a new graph. That would be the zoomed in version of the graph above. So in Plotly lingo, that would be changing the x-axis range and creating a new graph. So let's go ahead and do that. Okay, so again, we're going to start with adding some HTML. This is going to be our container div. Then we're going to add a new callback. And notice here, I'm going to use a different syntax for the callback. So here I'm going to pass a name function instead of using a do block. You'll see why. Another thing, I'm going to update two things. So there's two update types. And then this update close-up look like this. So there's a lot of boilerplate here. But the cool part with Julia, you could use multiple dispatch to kind of discard invalid values. So we know that a valid file name will be an abstract string, and then click data, we don't want to use blank click data. We want to use click data that's a JSON3 object, which is similar to a plain Julia dictionary. But this is the type that dash returns. So we use two methods. It's a nice way to do a validation at a really high level. So this is just boilerplate. So from the click data object, we'll try to pick our way to get a new x-axis range. Will look like this, and then with this new axis range, we'll create a new figure object, a new figure name tuple, and then using name tuple as argument splatting, it's kind of nice, I think. So name tuples are immutable, so you can't just mutate the new value in. You need to create a new one, but all the Julia's sugar makes it kind of nice. And then once we're done, we're going to output a new dash component here, a graph. So callbacks can output components, which is nice. And then I'll show you how this looks. Okay, so we're same graph, and then if I click on it, I get a close-up graph. So it's the bar I clicked on plus or minus 1 day, which can be convenient to view some sort of fault in more detail. Okay. Now, how much time do I have left? Okay, cool. Okay, so now we have our app. It's pretty good. But like I said, there's a bit of boilerplate involved, and we'll try to write it in a better way, in a more Julian way. So here, this is just highlighting the boilerplate that I'm calling the validation that we see often in callbacks. Okay. So one way to do it would be to come up with new types. This already feels pretty Julian. So I'm going to create a new abstract callback value. So callback value would be, you can think of it as the argument to our callback functions. And then the concrete types will be just wrapper structs around the values that we're going to use. So here in our app, we're using the file name. So this is fname. And we're using the point that we clicked on. Sorry, the bar. This could be, click bar would be a better name, actually. And then with these type, we can create, we create a function called from dash. So dash will get you something that comes from a JSON. And then what we can do here is have a wrapper function that will instantiate our new callback value types when that value coming from a dash interaction is valid, and output nothing if it's not. And that way we'll be able to do a multiple dispatch based on our new types or the nothing type. And if we go ahead and plug this into our app, so this is the update close-up, looking a lot easier to read, more maintainable, more scalable. So here we're, instead of dispatching on JSON3 objects and having to dig our way down to the values we want, we're just dispatching on click point and fname. We still have the fallback method. And then our callback looks like this. So I'm adding back a do function. You'll see why very soon. So here I'm just using from dash and then calling updates close up with our new types. And then it's pretty easy to go from this little piece here with the from dash method to a new function called add callback that will call from dash explicitly. And then we could pass in our new types in the input and the state definition, like this here. And so this way we can take in values coming in from dash that are JSON3, that are read using JSON3 into our new defined types. And then we could use multiple dispatch to simplify the logic. And I think I'm going to end here. All right, so any questions? Yeah.
As far as I understand, everything you said, it requires an active server to be running to deliver this data. Is there a way to save site state to a static file that doesn't require a server?
Is there a way? Okay, so the question is, if I got it correctly. So yeah, the demos I've used. So is there a way to use Dash without a server? Is that correct? Well, I guess you could. Short answer, no. You need a server running somewhere. In that particular example with the dropdown, you could have the data in the front end to start, and then have the dropdown select from data that's just in the front end, as opposed to making a request and then getting the data back. But yeah, you need a server running. Yeah, it's kind of you can think of it as a wrapper around HTTP, http.jl. Very high level wrapper. Yeah.
But once now shared publicly on like GitHub.io, and so it wouldn't have a server there. Do you have a recommendation how do you go to that? Because it seems static.
So your dropdown would be a list of URLs instead. Yeah, good question. I mean, I guess you could, but I guess you would also run into cross-origin problems sometimes. Yeah, I can't answer for sure, sorry. But good question, though. Yep.
Is there a way to take advantage of Julia structs that already have a show method for text HTML?
Say the last part again, sorry?
So if you define a struct and you can write a show method for like the MIME type text HTML, is there a way to take advantage of that, like get that to display in Dash? Okay,
so the question is there a way to reuse structs in Julia to have a show HTML method?
So for example, there's the package that uses. Is there a way to like... Yeah. Is there a way, and it's like a templating language for HTML. Is there a way to use something like HyperScript to create a bunch of HTML and then have that show up on a Dash page?
Well, not at a low level. I mean, there's a way to create your own components in Dash. But yeah, it's essentially you need to build a React.js component first, and then get that into there's a way to get that into a Julia package. So plain templating. I guess no. I guess you need a bit more for Dash to work. Yep.
So you have this callback bang method, right? That has you have multiple methods for that. Is that right? Because you have different input, output, and state arguments. Is that right?
Okay, so the question is, does the callback bang function have different methods? I think it's not. I think it's just one big argument splat. But
What's the relation between the inputs and the outputs you expect from your callback function? Is it always the same click and frame or something, wasn't it?
okay, so based on different output and input combinations, are we expecting a different behavior? Is that it?
From the callback, the actual callback function.
Right. So what Dash does internally is essentially serializes that into a JSON and then passes it to the front end. So whatever output you have behind the scenes, you'll get a JSON. And then the front end will handle that in JavaScript and then get it to render properly. So yeah, there's like, you could have one output or multiple outputs, so that changes a little bit what you get out of a callback, but that's about it. I don't know if that answered your question, but we could talk about it more. Cool. I'm done? Okay.
Yes. Cool. Okay, so we can thank Etienne for the presentation. And then I will ask the next speaker to come up front. So our next speaker is Luca Ferranti, and he's a PhD researcher in computer science at the University of Vaasa in Finland. And his research interests are mainly in scientific computing and in computational mathematics. He will talk today about fuzzylogic.gl, which is a package for productive fuzzy logic inference in Julia. Welcome, Luca Ferranti.
I have it. Okay. Yeah. Hello. Thank you, everybody. And I'm Luca Ferranti, and I will talk about fuzzylogic.gl, with this package which I have written for fuzzy logic. So, first of all, what is fuzzy logic? Well, if we think to traditional logic has only true or false, so it's like 0 or 1. Whereas in fuzzy logic, truth is between 0 and 1. So with fuzzy logic, we model vagueness, so if vague concept, which is actually how people think, how people behave. So for fuzzy logic, we model concepts like it's hot. What does it mean to be hot? If it's 30 degrees Celsius, yes, it's hot. But then if it's 29, suddenly it's not anymore. And 0 degrees is cold. Well, I'm from Finland, that's not for me, but 0 degrees is cold. But then if it's 15 in the middle, is it true or false? So with fuzzy logic, we have membership functions. So functions from a set to the interval 0 and 1, which tell us how much something is true. So for example, for the statement something is hot, we can have this S-shaped membership function. And if it's 30 degrees, yes, it's definitely true, 1. If it's 15 degrees, it's 50% true that it's hot. 50%, sorry, true that it's hot. So we have our basic building blocks, these membership functions. Then we can combine them with logical operators. And well, in fuzzy logic, logical operators are fuzzy because there's no one way to define like conjunction, disjunction, implications. We have some requirements. For example, for conjunction, for AND, we want a function which is called the T-norm. And there I have a few examples of T-norms. So minimum, product, or Lukasiewicz. They're the most common ones. But basically, we have a pool, a plethora of options to define how we define the AND, how we define the OR, and so on and so on. So that's like modeler choice, how to define that. And after we have done that, we can start talking about fuzzy inference system. So what is a fuzzy inference system? In the simple words, is a function which has some input variables and uses some fuzzy rules, to determine an output, which can be used, for example, for decision making. So if you want to decide based on your inputs how to control a machine or how much tip to give and so on. So let's, oh, nice slide. Let's see now a simple example. So this is kind of the hello world of fuzzy logic. This is a tipper system. So I want to decide, based on the quality of the service and the quality of the food, how much tip to give. And in the package fuzzylogic.gl, I have this domain-specific language to define fuzzy systems. So it's kind of fuzzy programming, if you like. So we have this @mumfis macro, which is to build a Mamdan inference system. Then we have a tipper called, takes service and food as input and computes the tip as output. Then for each membership function, for each variable, we define the membership functions. So service is poor, can be good, can be excellent. And for the food, similarly, runchy, delicious, and so on and so on. And then we write the rules. So we have that if the service is poor or the food is rancid, then the tip is cheap. If the service is good, then the tip is average, and so on. So that's the idea of fuzzy logic, that I write rules with words. So effectively, I do computations with words. If the service is poor or the food is rancid, then the tip is cheap, which is how humans work, how humans think, but now on a computer. Yep. Then, so that's probably not clear, the previous code. So in the package, you can plot the inference system. So just do plot fis, and it has plotting recipe, so visualize it. So we see now we have the rules and the plot of the membership functions. So if the service is poor, so close to 0, tip is rancid, close to 0, then the tip is cheap, so around 1, 2, whatever. And once I've constructed this fuzzy inference system, so this object fis, I can actually call it as a function. So I can do fis of service equal 2 and food equal 3, and it will compute the tip, like what is according to those rules, the appropriate tip. Yeah. Let's see now a nicer example. So I got this idea today while I was walking in front of the Julia Hub stand. So suppose we have an inverted pendulum, so a pendulum on a cart, on a car, and we want to balance it. We want to keep it in equilibrium. Without doing anything, if I poke the pendulum, it will start to have harmonic motion, as you know, so it will start moving and spinning around and around the pendulum. Now we want to define a controller for that, so to keep the pendulum in vertical position using fuzzy logic. And the cool thing is that we can do it with very little maths, with just intuition. So what is our intuition? That if the angle is negative, so I will want to poke the cart in the negative direction to balance it. Similarly, if it's positive, I poke in positive direction to balance it. And so that's what I encode here. I define my variables theta and delta theta, so angle and angular velocity. And if it's negative, so if theta is negative, the force will be negative medium. If the angular velocity is negative, then the force will be negative large. This is a very simple controller. Please don't use it in industry, just a proof of concept. But you can get the idea that modeler can use their experience, their human understanding, to define a fuzzy controller. So they know that if the angle is negative, the force has to be negative. And we write it this way, so basically in words. And then we can simulate it. So that was actually pretty nice, because it was pretty plug and play with differential equations.gl. So when I have the force, I just add my fis here. And then we see it works pretty well. So it keeps the angle to 0, so the pendulum stays vertical. Now, this is not perfect, because, for example, the cart will start moving, so you probably want to also balance angle and position. Yep. Then to conclude quickly, some other features. Maybe sometimes if you, for example, think to embedded applications, you don't want to run my package on embedded applications. So actually with the package, you can generate standalone Julia code, like optimized Julia code, and throw away my library, and it will still work. So once you have tuned your fuzzy model, you can generate standalone code. It can read standard industry, like MATLAB standard. So if you have worked in MATLAB, doing fuzzy logic in MATLAB, you can reuse your old codes, and you can just read it out of the box. And yeah, as future work, also like learning fuzzy models from data automatically, graphical user interface, and generate C code. Thank you for listening, and if you have any questions, please ask.
Why did you write the package?
I'll tell you also later, but I mean, mainly because I wanted to, because I was teaching a class in fuzzy systems, and so I wasn't very happy with MATLAB interface, and I wanted to write something different. And also, like in MATLAB, you used strings to select the algorithms, and I had this idea that in Julia would be nice because you can parameterize the fuzzy system by the type of the algorithm. And so at compile time, you can already choose what algorithm to use, and then at runtime, you don't have any branches, you already know like what algorithms it uses. So it was a nice plus. And also, Julia allows me to write domain-specific languages with macros. So yeah.
Does it compose into distributions.jl? Is that something?
I haven't tried yet, but maybe we can try. If you have an application in mind of how to compose it, would be fun to try. Yeah.
What kind of system are modeled by specific
popular application is in control theory, so like autonomous vehicles, autonomous objects. In image processing has also been used for like image denoising, in decision making, and in general like knowledge-based systems. So these are like those main applications.
So thanks for. So thanks to Luca Ferranti for his presentation. I will now introduce the next speaker. So he's a theoretical physics PhD at CTCP /NZIAS in Auckland. And he will speak about Markdown AST.gl, abstract syntax tree interface for Markdown. So please welcome Morten Pibelet.
Yes. Yep. Okay, cool. Hey, everybody. So, yeah, that information is slightly outdated. So I actually got my PhD. So I'm working at Julia Hub now as a software engineer. But this package was, this is something that was born last year after my PhD when I had a little bit of time. Fortunately, something I want to acknowledge here is the Julia non-focus grants as well, which sort of funded this project. So I'm really grateful for that. And yeah, so Markdown AST is a tiny interface package for Markdown documents. And some of you may know I also dabble with Documenter.jl, and so I want to motivate this package. Like the motivation of this package came from Documenter.jl, so I'm gonna explain the motivation of the package through Documenter. So if you know Documenter, it's a static. Well, if you don't know Documenter, it's a static site generator that we use to generate the manual of the Julia manual, and a bunch of packages are using it as well. And in a nutshell, how it works is takes a bunch of Markdown, you have your doc strings in your Julia code, and you have external Markdown files, right? And they get combined into the manual. That's what Documenter does for you. Technically, how it works is yeah, it takes the markdown. You first have to parse the markdown into some sort of a Julia data structure, which currently we use the markdown standard library that you have in that ships with Julia. That has a sort of a type of representation of markdown, and then Documenter takes that and does a bunch of processing on that. You end up with actually sort of a different representation of the, well, so the type of processing that the document does is like the example blocks get, like it evaluates code and does all those things and like cross references, resolves them for you and all that stuff. And then you end up with a different kind of representation of the document, which then gets passed on to sort of writer modules. So practically HTML and PDF are actually part of Documenter, but for the purposes of this illustration, think of them as like a separate step that comes after Documenter. And now this is fine. This is perfectly fine, this flow, but you want to do sort of more things with Documenter, hopefully. One thing you may want to do is some form of generated documentation. Like let's say you just want to generate some sort of page. It's not like a static markdown thing. It's something, for example, generated. One example of generated documentation is using literate.jl package, which basically can take those sort of Julia scripts that have a bunch of comments, and it turns them into documents. The comments become the markdown prose, and then like the actual code becomes sort of the code blocks or the example blocks. The way literate technically works right now is it actually turns those Julia scripts into markdown files. Those get then parsed, and that's how they end up in Documenter. But that's a little bit limiting because you have to actually produce markdown, which means you have to think about how to like represent everything in using sort of in the markdown syntax, and also you're limited to what markdown can do for you. So maybe we can do better there. Another practical example is like, well, what if we now have some other format that we want to ingest into Documenter? Could be something like restructured text, but like actually a very practical example is using Common Mark or GitHub flavored Markdown, because the Julia Markdown that we normally use is not the same as what you use on GitHub. There are differences, and this is the reason why if you try to load your standard README of your package README into Documenter, it doesn't actually look very nice because you're probably using some features of GitHub flavored Markdown that are not supported by the Julia parser. We do have a package in Julia called commonmark.jl, which can parse those things, but it has a different representation of the document, so Documenter has to add a support for a different representation when it starts combining all of these things together. What I would love, or like what Markdown ASD actually does now, and Documenter, like it has not been released yet, but on Documenter Master, it actually uses Markdown ASD internally. We take Documenter out from the middle and replace it with a standard representation, which is the Markdown ASD. And then things become much simpler. So if you want to have any extra formats, they become you just have to represent them in Markdown ASD, and then you can pass that to Documenter. Another example is, so if you have any generated documentation, you can generate the Markdown ASD of it, and it will become, and you can just pass that to Documenter. And then, Documenter takes the Markdown ASD, actually passes that back out, and then the writer modules can also use Markdown ASD. Everything is standardized, sort of documented. And so you have this nice interface now, rather than sort of ad hoc representations of these Markdown documents. Yeah. So what is the so briefly, like what is the actual representation, or how does Markdown ASD actually work? So if you do have a Markdown document, then well, if you're into computer science and parsers and stuff, and you know what an abstract syntax tree is, then you probably have a very good idea already what Markdown ASD does. But you can take a Markdown document and think of it as a tree. So this sort of document you could sort of think of it, it's a tree like this. So overall, it's like the root node sort of is, it's a document, and then you have like the top level elements, which is like the headings and a couple of paragraphs, but the paragraphs themselves are like sequences of like text, length text, and so on. So you get a tree kind of structure. So the natural data structure we want to use in Julia would be some form of tree. And yeah, so quickly just to show the implementation, you have the node type, which, so there's a type stable, so this provides type stability. So each of these nodes on the tree, once it's sort of been parsed, will be represented by a node type. And that contains all the information about like how to connect the different different nodes together. So you can traverse the whole tree, and it's a single type, so it's type stable. This is an improvement over the representation that's in the Markdown standard library, where things are sort of stored in vector any's all over the place, and it's extremely type unstable, and there are also no rules, and like the fields are kind of randomly named, and so it's actually pretty annoying to traverse the whole Markdown tree using the standard library. What Markdown ASD provides is so it has a bunch of methods and stuff that you can now use to work with these trees. Mostly to like modify. You may want to like say move around the paragraph or something like that. You can do that with Markdown ASD. It also supports the abstract trees interface. So if you want to traverse trees, you would actually use the pre-order DFS and all those algorithms that are in Markdown ASD. Oh, sorry, in abstract trees. The other part, the second pillar sort of in Markdown ASD are the elements. So every node has to have some sort of semantic meaning, right? So it's either a paragraph, it's either a link, text, whatever. So you will have the element field of every node contains all that semantic information, the contents of the code block, the language of the code block, all that information will be in an element, which is just going to be a Julia object attached to each of these nodes. So yeah, that's all basically. That's all I have. So my hope here, this is meant to be as a sort of a small advertisement. So if this piques your interest, please do get in touch. The package is obviously available in GitHub and in general and so on and so forth. My sort of long-term hope here is like short-term, it's already being used in Documenter. If at some point you may like, if you write any Documenter plugins or that kind of stuff, you probably have to deal with Markdown ASD. In the long term, though, if you work with any sort of documents that you want to like pass them around between different packages and that kind of stuff, so I do hope that this package could become the sort of the standard representation that we would use in the Julia ecosystem. So that's my hope in the long term. All right, I think that's all for me. So thank you.
Do we do questions?
You had in one of the first slides that Documenter can also output that format.
Yeah.
Is that the case already?
Yeah, so the question is there actually an EPUB output? So Documenter doesn't do that, but there is actually a package, like someone else is maintaining a package. I haven't really checked in on it. It was created a while back. So at least at some point there was an EPUB output for that. I don't know how well it works, but something exists.
Can you do footnoting now?
Question is, can we do footnotes? Footnotes are supported in the standard Julia Markdown, actually. So they've been there since the beginning.
Reference them in the text. I'll explain what I mean. When you have a link and then you have just a reference to the link, but you've got a list of links at the bottom of the Markdown, like a hypertext link.
You can do arbitrary footnotes, so like you can have a small block of text that is, and that has a small footnote label, and it'll jump down to the bottom of the page. So that actually does exist. And there's also a separate package that recently got a lot of motion, which is the Documenter citations, I think, which handles citations as sort of footnotes as well. But that's not quite the same thing, but that's also a cool package.
Probably end the questions here because time is running forward. So we will welcome our next speaker, who is a computational scientist and who is responsible for Julia computing at the Swiss National Supercomputing Center in ETH Zurich. He will talk about quick assembly of personalized voice assistant with just sailed.gl, if I'm pronouncing that correctly. So now, please welcome Samuel Omlin.
Yeah, hello, excuse me, his computer. So I hope he can quickly fix that.
There's another one. It's one from here.
Okay, this one should.
Is this some invite something?
Okay, great. All right, thanks a lot for being here. I'm going to talk about something very different that you have seen probably until now. It's about voice assistants, and it's about voice assistants with Just Say It, a Julia package. And concretely, I'll talk about the quick assembly of personalized voice assistants. So it's a flash talk, so I will do a flash introduction. So here you see two big numbers, right? And you guess, what is it? Well, it is the number of public and non-public GitHub repositories. And here you see the growth of GitHub over time, kind of exponential. And so why am I showing that? Well, it's impossible to create a voice assistant that would support all the software that exists in this world. And so there comes the idea from that we want to assemble our personalized voice assistant. And so I had a talk already last year at JuliaCon, and so I'll do a flash recap. It was about, well, a fresh approach to open source voice assistant development. You find the video on YouTube. And I showed that we can do very simple mapping of command names to functions or keyboard shortcuts. That we can do per command choice between maximum speed or accuracy. So for example, for a mouse click, you want maximum speed. Then smart speech to text. And fast command programming with voice argument functions. And so you see here in red this voice args macro, which allows for regular Julia functions to say a certain argument will come in by voice. And then you can give some additional keywords to define how exactly it should be recognized. And then so I said, well, we want to unite the Julia and Python communities by using Python functionality, in particular what you see in the middle there, WASC. It is a C++ library with Python bindings, which is doing the heavy lifting in the back. It's doing the voice recognition. All right, so much from the past. Now, how does it work concretely to assemble your personalized voice assistant? So you see here at the bottom, you see a dictionary, right? It says commands equal something. And so there is where we would assemble our global commands, so where we would specify what our voice assistant would do. So for example, you see there, we have some functions, which we will directly have available when we start our voice assistant. You see, for example, ma there for a left mouse click, right? And then below you see, we have, for example, we say terminal, and then it would open a terminal. And so on the right, you see what it would do. Or we say coding, and it would open VS Code. And so you see there we have actual commands, like Julia commands to the type commands, CMD. And on the right, we would have a dictionary which would specify all the commands that will be automatically activated as soon as we start, well, VS Code. Now above, you see so this VS Code commands dictionary that is given there in the global assembly, it's just another dictionary, right? Which in this case will be just created by merging other dictionaries. And concretely, so in the second dictionary that you see in this slide, we will have some specific commands for VS Code. So for example, jump to line, and then this would automatically trigger a sequence of actions. So it would do Control P, then write a colon, and then this type digit string would mean that you say the digit, right? And then it would do enter. So you just say jump to line 345, yeah? And then, for example, below peak definition, in order to see the definition of a certain function or whatever, right? And then on the top, you see some generic dictation commands, which will be usable in most applications, not only in VS Code, for example. And so this means, just like we define here commands for VS Code, we'll define commands for the terminal, for internet, for anything. We will use specific commands plus generic commands. And then, once you've done that, well, you will just do this, use just state, using just state, and then start using these commands, right? Passing it to the start function. And this will start your personalized voice control or voice assistant. Now, on just say recipes, we can share, on this repository, we can share such kind of recipes to create personalized voice control, because you don't want to do everything from the bottom up yourself, right? You want to share it with others. And right now, we will already find one example there. Yeah, so this was the global idea of how you create your voice assistant. And now I will show you just a little bit what's behind also. So the power of dynamic recognizer creation. And so, for example, if you want to type this here, what you see, you would say letter A equal digit 34 plus letter B. Yeah? And then it would type that. Now, what happens behind the scene? At first, you have like a basic command recognizer, which will deal with letter A until equal. And then afterwards, digits is actually a function, as we can create function for anything, which will just understand 0 to 9. But in addition to that, we will add automatically, dynamically, what was said before, such that we have a smooth transition between the recognizers. Because if you would just cut off the audio, you would not be able to accurately recognize the things. And then, so this digit function will exit when it doesn't understand the next word. And we will go back to a command recognizer, which in addition to what it was able to understand before, would also be able to understand the digits that were just said. And so still guarantee a smooth transition between recognizers. Now another quick example. So it's about smart copying. We can very smartly copy things by saying, for example, here, we have this text in the first line, and you see that the red thing there is the cursor. And let's say, okay, take, write, assembly till assistance. So it would copy everything from assembly to assistance. How is that done? So it would select from the cursor until the end, like this. And then it would create a recognizer using the content that is marked there. And with that, understand what the user said. And then afterwards, well, select and copy the desired substring. And so this shows that for very complex tasks, we can still very accurately recognize things, because we can make very specialized recognizers that only understand, or that exactly understand what they need to understand. All right, conclusions and future work. So we developed some unprecedented, highly expressive and effective way to assemble personalized voice assistants. Just say it uses a powerful recognition approach based on dynamically created specialized recognizers. And we have this repository here to share recipes. Now, very quickly about future work. It is my idea to leverage large language models like ChatGPT. I hope to finish something until this conference, was not able to. But next year, you will have something. And also, of course, I would have a little bit better, I would like to see what is happening when we say a command, so to have like some subtitle-like appearance of what command is executed. All right, so that's all. Please check out the talk from last year, and here is the repository.
Yeah, we may have time for one quick question. So, yes,
I have two. How fast is it, and do you use it in your own workflow?
Yes, actually, I use it every day because I had a problem with my hands, and well, it's not completely fixed, but it's getting better. But so yeah, I mean, I've developed that for that reason since more than 2 years. And fast, if you set this accuracy thing there, this is what I said in the recap, that you say max speed instead of accuracy, then you can have mouse clicks which are instantaneous.
Thanks a lot to Samuel Edelman for his presentation. I will now ask the next speaker to come at the front. So our next speaker is a technical analyst at Rand Corporations. His work focuses on machine learning, modeling, and simulation. He holds a master science degree in applied mathematics from Stony Brook University. And he received an award for investigating distributional shifts. So he will talk about Julia through the lens of policy analysis. So please welcome Joshua Steyer.